it's a couple of sentences. So, hello. We are going to get started. So, it is my actual great pleasure to introduce today Tamara Broderick, who is going to talk us about variational Bayes and beyond, and how to apply it for big data. And as most of you may know, she's an assistant professor at MIT, and she got her PhD from Berkeley. In principle, she's not going to make a break during the talk, and we are going to postpone all the questions for the end of the tutorial. You will have two mics, one that I'm going to move later on over there, and another one over there where you can queue to ask your questions at the end of the tutorial. And okay, help me welcoming Tamara.
Okay, thank you. It's great to be here, and I'm excited to talk to you today about how we can perform Bayesian inference for our modern large data sets and large analysis problems. So let's start by talking about, how is Bayesian inference being used in practice? So you may have noticed that Bayesian inference has been used in some of the big scientific and related discoveries of the past few years. So for instance, there was this TRAPPIST-1 exoplanets discovery. And in this case, Bayesian inference was used to get point estimates and uncertainties about candidate observations, and thereby decide if these were really exoplanets. Bayesian inference was used in the gravitational waves discovery. In this case, it was interesting to get point estimates and uncertainties about aspects of the black hole that was emitting gravitational waves, things like the mass and the spin, to know not just what do we know, but how well do we know it. Tragically, in 2009, a passenger plane crashed over the Atlantic Ocean, and for years, people were trying to find the wreckage of this plane and not having any success. And then sort of miraculously, they brought in Bayesian inference a few years into this search, and after they started searching again with this new statistical set of tools, they were able to find the wreckage in about a week. So if we look at transportation analysis, so Dawn Woodard is the senior data scientist of maps at Uber, and she and many other people are looking at Bayesian inference for routing, for understanding what are the times for vehicles to get between different areas. So this could be ambulance routing, this could be other types of vehicles. And in this case, it's really helpful to know not just how long we expect a vehicle to take to get to a certain point, but also how certain we are of that. What's our uncertainty about that timing, which is very important if we're doing some kind of planning. Rachel Meager is an assistant professor at the London School of Economics. So there she's studying microcredit, these small loans to individuals in impoverished areas. And a very important question is it actually helping? Is it helping bring people out of poverty? Is it helping the situation? And so there we want to know things like, well, how much is it helping? How much is it increasing business profits? And it's important to say not just how much is it increasing business profits, but how certain are we of that value? What's our uncertainty about that value, especially, again, if we're going to make decisions based on this? Like maybe we might make some sort of philanthropic investment or something of that nature. Yashavardhan Chadi and Hamsa Balakrishnan at MIT are interested in predicting how much fuel a plane is going to use based on publicly available information about that plane. And in this case, again, we want to know not just how much fuel that plane is going to use, but how certain are we, especially if we're going to make decisions based on that information. In fishery management, Bayesian inference is very often used because we really care about risk management. Overfishing is a major issue these days. It's possible to have population collapse in a fishing population, and then we don't have any fish anymore. And so we want to be able to, when we're managing these fisheries, keep in mind that type of risk. Okay, so in all of these cases, there are a very similar sort of set of analysis goals. We really care about not just what do we know, but how well do we know it. So we want to get point estimates, and we want to get uncertainties. And typically, there are many unknowns in a different model, in a given model. And so we want something that's coherent across those unknowns, uncertainties that are coherent across those unknowns. Also, typically, we're interested in pinpointing some particular aspect of this analysis and really understanding it, and so we want interpretability in that sense, that we can pinpoint, here's the quantity that we want to understand. We want to build up complex models of physical phenomena, or social phenomena, economic phenomena, engineering phenomena. And so the graphical models framework that Bayesian inference works in, the modularity of that framework lets us build up these complex models. And finally, in all of these cases, we see that we're working with experts. Experts are working on these problems. They have a lot of domain knowledge, a lot of knowledge that they can bring to bear and should bring to bear on these problems. And so it's nice that with Bayesian inference, we can incorporate that kind of expert information. Okay, so now we've gone over at this point sort of a lot of example applications where Bayesian inference is being used, but just to get a scale of, a little bit of a scale of how often these methods are being used, let's notice that there are a lot of probabilistic programming languages these days, a lot of probabilistic programming languages that let people use Bayesian inference in a relatively automated kind of way. Just one of them, among quite a number, is Stan. Stan works with Julia, it works with R, it works with Python, MATLAB, and so on. If we look just at R and we look at just one download mirror on R, Stan is typically downloaded in a given month over 10,000 times, well over 10,000 times. At about 300,000 times, if not more, since 2015. And so this is something that is being widely used in the sciences, in engineering, in the social sciences, as we said before. And so we want these tools to be as useful as possible to people. We want them to be something that people can use, that they can rely on, that is easy to use. Now, unfortunately, a lot of existing methods are sort of overly slow. You talk to people who are using Bayesian inference, and it can be taking days, if not weeks, for their methods to run, for their approximate Bayesian inference methods to run. And so something that we really want to be able to provide to them is something that's much faster. I mean, for one, a lot of problems actually have a real-time sort of component, but in general, this is time that they could be spending on, their actual research in the sciences or whatnot. Okay, so we want methods that are fast for these users. That's a big, outstanding challenge here. And when I say that they're fast, I mean two different things. So of course, I mean computing time. I want these methods to be able to run quickly. But I also mean user time. So we don't want a user to have to sit down and, tediously derive a bunch of equations and, updates for their algorithm, or do a bunch of sort of hyperparameter tuning at length. We want them to be able to focus on the biology problem, the chemistry problem, the economics problem, and not this type of problem. So we want something that's fast in user time. Okay, well, there are plenty of algorithms that are fast in computing time and fast in user time that are just wrong. You could just return the number 5 if you didn't care if it was right or not. So of course, we also want it to be reliable. We want our algorithm to give something that we can actually trust at the end of the day. And so this is sort of the challenge. We want something that's fast in computing and user time, that's easy to use, that's reliable. Also, I'm just going to mention there's sort of this fallacy that I think people think about sometimes, this idea that, well, we don't care about uncertainty because our data set's so large. Now, sure, if you have, one tiny little thing that you're trying to learn and all of your data is informative about it and you have millions of data points, that's true, but that's not typically the situation that we're in these modern large data problems. Typically we have a ton of data and we're trying to learn more as we get more data, more nuance about our data, or more different types of things that are going on in our data. And so we still have uncertainties and we still want to quantify those uncertainties. Okay, so what do? How do we deal with this problem? How do we have fast Bayesian inference? Well, certainly something that people have increasingly been turning to over the past few years is variational Bayes. Why are they turning to variational Bayes? Well, it seems like it's addressing these modern problems, these problems with a large amount of data and a large size in the problem, something like a large dimensional problem. And in particular, it seems like it can do this very quickly. So variational Bayes has been applied in a lot of areas. Sort of the canonical area that I think we see it being applied is in text analysis. There's a ton of text data nowadays. Even if you don't have access to proprietary text data, if you just look at what's online, there's a ton of text data there. You could spend all day analyzing it. And it's a very sort of large problem. There are many topics that we could pick up in this text data. We want to find the assignments of words to topics. We want to find all of these things. And variational Bayes has enjoyed a lot of success in this area. Now, variational Bayes isn't just used there. It's also used in things like discovering structure in networks or graphs. This is another type of data that's increasingly growing in popularity. Maybe we want to find communities or find some other type of structure. Variational Bayes is used in neuroscience, in gene expression analysis, and other areas of computational biology. So it's used in a lot of these sort of, important cutting-edge areas where we want to do scientific analysis. And so it seems like it's worth studying what's going on with variational Bayes. Okay, so in the rest of this talk, we're going to first spend a little time recalling to ourselves what is the goal of Bayesian inference? What are we trying to do with Bayesian inference? And in particular, why are we going to approximate Bayesian inference? What's the goal there? What's our approximation goal? Along the way, we'll start talking about what is variational Bayes, what is mean field variational Bayes, a particular type of variational Bayes that's very popular and very widely used in practice. And at that point, we're going to focus on mean field variational Bayes as a little bit of a microcosm. Why use mean field variational Bayes? Why is this so popular? Why is this widely used in practice? And then, can we trust mean field variational Bayes? Should we always be using mean field variational Bayes? Is this sort of a panacea? And then finally, in the second part of the talk, so this is essentially the first part of the talk, in the second part of the talk, we'll ask, where can we go from here? Sort of probably unsurprisingly, any method that we have nowadays has challenges, it has pitfalls. We'll go over those pitfalls, and then we'll think about, how can we address those? So we're going to start, again, thinking about Bayesian inference. What is Bayesian inference, and what are we trying to do with Bayesian inference? Okay, so with Bayesian inference, the first thing that we want to identify is our unknowns, our parameters. These are the things that we're really interested in or we don't know about our problem. So for instance, let's think about that microcredit example from before. Maybe we don't know how much microcredit is increasing business profit in each country that we look at. We don't know how much it's increasing business profit across all the countries. We don't know the base business profit in each country. We don't know the base business profit about all the countries. There are plenty of other things that we don't know, and so we collect them all in this high dimensional, or at the very least moderate dimensional, parameter vector, let's call it theta. And if we're taking a Bayesian approach, then we start off by saying that we know, or maybe we don't know that much, either way, we express that knowledge or lack of knowledge in a distribution, in a probability distribution called the prior distribution over the parameter. Okay, now something that we're going to deal with repeatedly in this talk is the fundamental limitations of our human eyesight. So a problem with us is that we can only see in 2 dimensions. And so it's hard to actually look at this high dimensional distribution that we're dealing with. And so here I have a cartoon of a prior where we have sort of a diffuse distribution over theta, but you want to keep in mind that actually the type of distribution that we're dealing with, the type of parameter that we're dealing with, is actually moderate if not high dimensional. Okay, so we have this cartoon of our prior, we've collected our prior. Next, we want to get our likelihood, or at least at the same time we want to be choosing our prior and our likelihood. So our likelihood tells us how our data interacts with our parameters. So here, we're going to call our data y, and we're going to imagine that we have capital N data points, y1, y2, y3, up to y capital N, and I'm going to abbreviate that collection of data as y1 colon n. Okay, so our likelihood, again, tells us how this data relates to our parameter theta, and together, the prior and the likelihood make our model. This is something that's traditionally been called a generative model. I just want to point out that this is a different usage than you may be seeing in modern machine learning a lot of the time. But this would often be called a model or a generative model, these 2 choices. They tell us how we could simulate from our data. But of course, we don't simulate our data. We actually observe our data. And so what we do is we notice that what we've established here at this point is a marginal, the prior, and a conditional, the likelihood. And so that just makes a joint distribution. And so another way that we could look at a conditional that comes out of this joint distribution is to condition the theta on the y's. And that's called the posterior distribution. This is just a fact of probability that we've used, and this fact of probability is typically called Bayes' rule or Bayes' theorem. So now what we have at the end of this is, what do we know about this parameter, this set of unknowns, now that we've observed the data? And the typical cartoon that we imagine in this case is that we start off knowing relatively little about theta going into our problem. We apply Bayes' theorem after getting our data, and then we hope that we know more about theta. And the way that we can express knowing more about theta is that it seems like our variance has decreased, our uncertainty has decreased in this distribution. Okay, so let's just summarize here. What are the steps of Bayesian inference? 1, we build a model. We choose a likelihood, and we choose a prior, and that's our model. 2, we compute the posterior. We apply Bayes' theorem. And now at this point, we recognize, again, it's going to be hard, especially if we have a high-dimensional parameter vector or something like theta, to actually plot that posterior, to really look at that posterior in any depth. And so a typical thing that we might do at this point is we might say, hey, well, we got to summarize this somehow. We've got to report this somehow to people at the end of the day. And so a typical summary that we might look at is something like a point estimate and an uncertainty. Now, there are a lot of different ways that we could report this point estimate and uncertainty, but certainly a very popular method, a method that has a lot of sort of statistical and theoretical backing for it, is to report a posterior mean as our point estimate and posterior variances or covariances as our uncertainty. And so this is what we imagine doing at the end of the day, is making this report. Okay, so now something that's worth realizing is that each of these steps presents a challenge. We have to build this model, first of all. We could have a whole tutorial about building models. In this case, in the case of this tutorial, we're going to focus on the computational aspects. We're going to suppose that somebody has given us the model. A practitioner, or somebody else has given us the model. They've given us the prior. They've given us the likelihood. And we want to report back to them the mean and the covariance. This would be a typical perspective that we might take, for instance, if we were a probabilistic programming language. Okay, so I said that there was a computational challenge. Where does the computational challenge come in? It's in steps 2 and 3. So let's take a moment to think about, why is there a computational challenge? Why are steps 2 and 3 difficult? Well, first of all, even though this Bayes theorem is just a fact of probability, that doesn't mean that we can get out a nice form for the posterior, a nice closed form, some sort of distribution that's very familiar and easy to us to work with. In fact, in general, that won't be the case for any sort of moderately complex model. That won't be the case. We're not going to get that closed form. And now, what we're left with is a moderate to high dimensional integration. So if theta is high dimensional, then this is going to be a high dimensional integration. Why do we have a high dimensional integration? Well, remember, we're reporting a posterior mean or covariance. To get a posterior mean, that means integrating theta over the posterior. Another way to look at this is just even to get the posterior, we have a high dimensional integration. So in particular, let's look at that normalizing constant. So right now we just have proportional to, but we can actually write out the normalizing constant here. So the way we get this is we just say, hey, this is just a marginal times a conditional. Here's another way to write a marginal times a conditional. Here's the normalizing constant. And this is often given a name. It's called the evidence. The probability of the data is called the evidence. Well, how do we get the data, or how do we get this probability of the data? How do we get the evidence? Well, remember, the only thing that we start off with is the prior and the likelihood. That is the input. That is what we are given to start with. And so we have to get anything that we do from that. And in this case, this marginal is just the joint with theta integrated out. And this joint is just the prior times the likelihood. And so that's where we have our high dimensional integration theta. That's a hard problem. Integration in more than 1 or 2 dimensions is a hard problem. And that's fundamentally the issue that we're dealing with today, is how can we do something like this integration? Okay, so now let's start thinking about, well, how would we actually deal with this? This is where the approximate Bayesian inference aspect comes in. Now, traditionally, the gold standard for this has been Markov chain Monte Carlo. It's been called one of the 10 most influential algorithms of the 20th century. It's extremely widely used. And in particular, one of the reasons that it's widely used is that it's eventually accurate. If you run it long enough, we know that you're going to get the right answer for your integration. Of course, the problem is you might not have until eventually. If this takes a week, if this takes a month, if this takes the age of the universe, then that's going to be a problem for your analysis. And so increasingly people are saying, gosh, my method, it's running too long. If I use Markov chain Monte Carlo, what else is there that's out there to get this integration, to get this approximate Bayesian inference that I want to calculate these means and these covariances? And so one observation here is, gosh, something that's really sped up a lot of inference, a lot of machine learning procedures over time, is to use some form of optimization. How about we use some form of optimization here? And so here's an idea to take an optimization approach. So remember, the idea that we're approaching here is we say, okay, let's find some approximation to our posterior. Same thing we do with MCMC. We're finding some approximation Q star, and then we're going to use its mean and its variance as approximate means and variances for our exact posterior. Okay, so now we're going to say, though, that we're going to find this Q star with an optimization approach. So suppose there's a lot of distributions out there in the world, and there's a set of nice distributions. What do I mean by a nice distribution? What would make a distribution nice? Well, remember, we have a specific goal at the end of this. We want to report a mean and a covariance. And so if we can calculate a mean and a covariance for our distribution, that seems to make it pretty nice to us. So let's assume for the moment that we have this vague definition of nice, that this is a case where we can calculate a mean and a covariance for these distributions. And of course, the whole problem, the whole reason that we're talking, is that our exact posterior is not a nice distribution. We cannot easily calculate means and covariances for it, and that's why we're in a bit of a pickle. So we might say to ourselves, well, maybe the way that we can deal with this is we can approximate our exact posterior, which isn't a nice distribution, with the closest of the distributions that are nice. And so now we have something that's starting to look like an optimization problem. We want to find Q star out of all of the nice distributions, let's call them capital Q, such that it is the least far. So we have farness represented by this F. So we want to find the closest of the nice distributions. Well, there's a reason that I'm avoiding the word distance here, because distance has a very particular meaning. So distance means that F is positive definite, and it's symmetric. And actually, we're not going to make that assumption here. We're going to assume, in fact, if we use variational Bayes, that F is not symmetric, that it's the callback-Liebler divergence in a particular direction. Okay, so that's an interesting choice. We're choosing a divergence rather than a distance. We're not choosing a metric here. So we're going to spend a little time thinking about, well, why would we do that? There are plenty of actual distances between probability distributions. We could have chosen Wasserstein. We could have chosen total variation. We could have chosen all kinds of other things. And for some reason, we went and chose the callback-Liebler divergence. So let's think about that for a bit. So first, let's just think at a very high level. Why might we have done this? Well, one reason is that it seems like people are using it a lot. So maybe we should just understand it from that perspective. It seems to enjoy a reasonable amount of practical success. We seem to get point estimates and predictions that are pretty decent. It's certainly very fast. So one piece of work that just happens to be ours, this is not the only piece of work demonstrating this is fast. We show that we can make it streaming, we can make it distributed, we can run on millions of Wikipedia articles with 32 cores in about an hour. And this was back in 2013. There's been a lot of other things going on since then. We can be even faster. This is a very fast method. And so that seems very promising, because that was the whole point, right, is that we found that our existing methods were too slow, and we really wanted to speed things up. And so we asked ourselves, what can we do? How can we get faster? Okay, so that's at least a little bit of a motivation to keep thinking about this. But let's think a little bit more deeply. Why KL divergence? Why can't we do this with other forms of distances or even other forms of divergences? So in order to start answering this question, let's actually write out the KL divergence. And remember, it's not symmetric, so we're writing out in this particular direction used by variational Bayes. Okay, so the KL divergence is the integral over our approximating distribution of the log of our approximation divided by our exact posterior. Okay, now I'm going to ask you a very real question that I'd like you to think about, to yourself for just a second. Suppose that I had a perfect optimization algorithm. If you give me the form of the optimization, it will return to you the exact optimizer. And so I tell you, hey, here's my KL divergence problem. Tell me the optimal Q. Can you think about a reason, just think to yourself for a second about why this is not practical at this point? Okay, so one thing that you may have noticed is that this requires knowing the exact posterior, and that's kind of a problem because the whole point was we don't know it, right? So if we want to optimize the KL divergence to the exact posterior, the optimal value, because this is a divergence, it's positive definite, is, in fact, the exact posterior, but we don't know that. And in fact, this is going to be a problem not just with the KL divergence, it's going to be a problem with any distance, any divergence we might choose. If we're trying to find the closest thing to the exact posterior and we don't know the exact posterior, how will we ever have any hope? This seems like a chicken and egg kind of problem. So in order to think about how could we possibly get around this problem, let's do a little algebraic manipulation. So in particular, what I'm doing in this line is I'm just knowing that the posterior is a conditional, so we can just write it as the joint divided by the marginal. So that's what I'm doing here. I'm just writing the posterior as the joint p of theta and y divided by the marginal p of y. And now we're going to use some logarithm facts. So remember that log of a times b is log of a plus log of b. So we're going to get an integral over q of log p of y. But q is a distribution. And so that integral is going to be 1. So we're just going to be left with log p of y. And then, to get this term over here, we're going to remember that log of 1 over a is just negative log of a. Okay, so together with those facts, we've written out our optimization objective in the following form. And now let's focus on these two terms that we're summing in this objective. So the first term, log of p of y. Remember, we are minimizing the KL divergence over q. This term does not contain q. And so if we're trying to find the q that minimizes the KL divergence, we can just throw this term out because it affects nothing. Okay, let's look at the second term. What's the thing that we're subtracting? Well, this is pretty nice. Now this second term contains only things that we know. P of theta and y, the joint P of theta and y. That's just the prior times the likelihood. Those are exactly the inputs that we put into this problem. So sure, we might still have an issue of, how do we optimize this? What's the best way to optimize this? But things are looking at least like they could be optimized in this case. This has a hope in the way that just having a general distance here seems possibly hopeless. Okay, so this is so important. This thing that we actually can optimize instead of the KL, that it's given a name, it's called the evidence lower bound, or the ELBO. The ELBO just being an abbreviation for evidence lower bound. Okay, so something that I think is pretty useful if you really want to learn in areas to do some exercises, and so I'm going to suggest a few along the way. I'll also suggest some reading later on. But the first exercise that I'm going to suggest is that you can actually show that the KL is greater than or equal to 0. In fact, you can go further than that. You can show this is positive definite. The KL is always greater than or equal to 0, and it's equal to 0 exactly when the inputs are the same. If you have any trouble with this, just look at major textbooks in this area, like Bishop's textbook, his pattern recognition and machine learning textbook. But it's worth spending a little time, at least trying to do this. Now, once we know that the KL is non-negative, we can use the relationship that we just described to show, very simply, so this should just be immediate, that the log of the evidence is greater than or equal to the ELBO. So this is just a way to explain where did that ELBO name come from. Well, this is clearly a lower bound for the log of the evidence. Okay, but the really important point here is that minimizing the KL, finding Q star to be the minimizer of the KL, is exactly equivalent to finding Q star to be the maximizer of the ELBO. We didn't make any approximations. This is essentially the exact same problem, at least in terms of the Q star that we get out in the end. Okay, so now let's ask ourselves again, why KL? Why KL in this direction? Well, we had this super cute derivation, this super easy derivation where we were able to get rid of the thing that we hated, this normalizing constant, the thing that was really slowing us down. And it really seemed to have depended on the form of the KL. Now, that's not to say you couldn't do something else with another type of divergence. Certainly people look at other types of divergences. Maybe you could bound it, maybe you can get some approximation, but this is very convenient. This means that we can actually solve this problem. We can actually minimize this KL divergence exactly, at least up to this point. We haven't had to make an approximation. And why KL in this direction? You can't pull this trick in the other direction. In the other direction, the integral is over the exact posterior, which we don't know. So it's really this trick, this ease of use, that led us to choose KL. Okay, so let's think about where we are at this point. We had this sort of not fully formed optimization problem. We said we wanted to find the closest of the nice distributions. Now, we so far have defined a notion of close. We're trying to minimize the KL divergence, but in order for this to be a well-defined optimization problem, we still have to say what it means to be a nice distribution. So let's think back to ourselves. What was the goal of nice distributions? What were we trying to accomplish with nice distributions? Well, we were trying to report means and variances. So what types of distributions let you report means and variances? So let's think about how are we going to choose these nice distributions Q. Okay, well, I think that there are sort of two answers that immediately come to mind when you think what types of distributions let you report means and variances relatively easy. The first one is low-dimensional distributions. It's really these moderate to high-dimensional distributions where we have trouble with integration. Low-dimensional distributions aren't much of a problem. And so this is a way to motivate one choice that we might make for the nice distributions. When we make this choice, when we say that our Q, our nice distributions, factorize in this way, we say that we're doing not just variational Bayes anymore, but mean field variational Bayes. Okay, so what's going on here? So we're imagining that we have our parameter vector theta. It's maybe very high dimensional, but it breaks down into components. So it has components, theta 1, theta 2, theta 3, up to theta capital J. They don't have to be one-dimensional, but we imagine that they're smaller and easier to deal with. And we assume, moreover, that our approximating distribution Q of theta factorizes over these theta 1 up to theta j. That is the mean field variational Bayes assumption. Okay, now I said that there were two answers to what makes a nice distribution. When can you calculate means? When can you calculate variances with a distribution? I think another perfectly valid answer to that would be exponential families. Exponential families are great. When you have exponential families, you can do whatever you want. Especially if what you want is reporting means and variances, then that is the thing that you can do, and quite easily. And in fact, often when people say that they're doing mean field variational Bayes, they mean the combination of these assumptions. They mean that we're going to assume that our distributions factorize, and we're going to assume that they factorize into convenient, familiar exponential family distributions. Okay, now something I want to emphasize very much here is that this is not a modeling assumption. We went into this talk saying that. We imagine somebody has come to us and they have given us a prior and a likelihood. That is our model. And we want to have an automatic way to report back to them a posterior mean and a posterior covariance for that choice. And we would not like to limit them in that choice, at least as much as possible. And this would be an extremely limiting assumption in actual models. This would basically restrict us to models that are super boring and nobody uses them. We do not want to make the assumption in our models that there's some independence going on between all of the parameters, and we're not doing that. We are only making the assumption that our approximation has this factorization assumption. Now, we can still ask, is that a good approximation? And in fact, we will. We're going to spend a lot of time asking that question. But we are not making an assumption about the model itself. There is an exact posterior, and we are trying to approximate it. Okay, now at this point you might be thinking to yourselves, this is still a really weird approximation, right? I mean, we are just assuming that everything is axis aligned. Is that ever going to work out? And again, we're going to spend some time thinking about that question, but just to sort of assuage your interest for a moment, here is a very simple example. Again, we can sort of only see in 2 dimensions, so if I want to show you a distribution, it's got to be in 2 dimensions. And so what we're seeing here is a case where we're looking at an exact posterior. The contours of the exact posterior are in green. It is a 2-dimensional distribution. And we can apply mean field variational Bayes to this distribution, and the contours of the mean field variational Bayes approximation are in red. And I think the thing that's worthwhile about this picture is, hey, this doesn't look totally weird. It looks like the mean field variational Bayes approximation is actually decent. The means aren't probably too far off from the actual posterior means. The variances, the uncertainties probably aren't too far off from the actual posterior uncertainties. So maybe this is something that could work. We'll keep asking that question. Okay, so now we have an optimization problem. We have a well-defined optimization problem, finally. We're trying to find the closest of the nice distributions. Our notion of close is this KL. Our notion of nice is a mean field variational Bayes. How do we solve it? In some sense, any way you want. So at this point, once you have an optimization problem, you can use the latest optimization technologies. You're not limited to anything in particular. We're going to talk about some methods to solve it, but not in a lot of depth. And it's more like I want to say you could use whatever technology you want. What we want to really examine is this optimization problem that we've set up. So one way that you could do this, a very classic way, but certainly not the best way on its own, is coordinate descent. So you can just go through each one of the queues in turn and optimize the queues. Again, this isn't the best thing that you could do. It's just an option. There are many options. It's an optimization problem. Okay, so let's review where we are at this point. We decided that we were going to try to do approximate Bayesian inference, and then we made a bunch of choices. And it's worth being cognizant. It's worth being really clear about what those choices were. And I'm examining our assumptions, examining those choices. So the first choice that we made is sort of a very subtle one. We chose to approximate our posterior with another distribution. If we're just going to report posterior means and covariances, technically speaking, at least a priori, we don't necessarily need to have done this. We could have done some other way to just get at those values directly, but this seems to be the approach that we're taking here. Okay, the next choice that we made was to take a certain style of optimization approach. We said, hey, the way that we're going to find this Q star that approximates our exact posterior is we're going to minimize some notion of divergence over nice distributions. So at this point, we haven't said exactly what those are, but it's still a choice. We could have done Markov chain Monte Carlo, which doesn't fit into this framework. In fact, there are other things that don't fit into this framework. If you're familiar with the Laplace method, it doesn't fit into this framework. We could have just found the maximum posterior estimate. We could have said what value of theta, what value of our parameters maximizes the posterior, and done sort of a local perturbation around that to get a Gaussian approximation. That's the Laplace idea. So there are other methods of approximation we could have used. This was a choice. Okay, then we said, hey, let's use the KL divergence. As our notion of divergence, we're going to use the KL divergence. We didn't have to do that. We could totally use other divergences. In fact, sometimes when you're reading papers, you might find that people refer to the general optimization problem as variational inference. As long as you're clear what you're doing in your paper, that's what matters. But here we decided to use the KL divergence. Okay, then we said, what are the nice distributions? How are we going to optimize over those? We made a choice. We said that we were going to use mean field variational Bayes. We were going to use this factorizing assumption and typically also make an exponential family assumption. That was a choice. We didn't have to do that. We could have considered other types of things to optimize over. One in particular would be something like optimize over all of the normals. All of the normal distributions that are the size of our full parameter space. Okay, and finally, once we've made all these choices, we can choose how to optimize this problem. And there are many different choices we could make there. So one is coordinate descent, but it's certainly not the only one. Something that people have noticed is that if you use coordinate descent, this is actually still pretty slow. And so an observation that people have made in general in machine learning is that stochastic gradient descent seems to really speed things up. And so if you use stochastic gradient descent in a sort of unusual way, you can apply it in this case. It's a little bit unusual, but you can apply it, and you get something called stochastic variational inference. Another issue, again, is this issue not just of computing time, but of user time. So if we just do mean field variational Bayes coordinate descent, it turns out we have to sort of hand derive an algorithm, much like Gibbs sampling. We have to figure out exactly what the steps are. That could be a big pain for a user. And so another option is to just assume that every marginal is Gaussian, that all the distributions are Gaussian. And then it turns out we can automatically do this with the magic of automatic differentiation with automatic differentiation variational inference. Okay, there are a lot of other choices that we could make for optimization here, but all of them, when we apply them to the mean field variational Bayes problem, are still mean field variational Bayes. And so it's worth our time to understand not just the optimization procedures we're using, but in fact, what is the problem we're even trying to solve, and is it doing what we want? And so that's what we're going to spend some time on now. Okay, so we talked about Bayes and approximate Bayes. We've defined variational Bayes and mean field variational Bayes. And so now let's think a little bit about, is this something that we should be using? Does this ever work? I mean, it is a pretty restrictive assumption, this factorization assumption. And so we want to know, is it ever going to give us something actually useful, especially in complex models? So we're going to start off with a very simple model. So midges, you might be familiar, are these small winged insects. And in general, when biologists might be going out and studying different species or genuses, they might want to get a sense of sort of what's going on with animals, with individuals within that species. And so scientists have actually sort of measured a bunch of midge wing lengths, and maybe we want to learn more about those lengths. And so a model that we might have is that these midge wing lengths are normally distributed, with some mean mu and some variance sigma squared. We might think that this is a reasonable model, maybe because we think there are a bunch of sort of genetic and environmental factors that maybe have some kind of linear way that they add up, and we get a normal distribution. So in this case, we have a very simple set of parameters, mu and sigma squared. That's our theta in this problem. So we're interested in this theta, that's mu and sigma squared. We have this, we have part of our model. We have the likelihood, but remember there's two parts to our model, the likelihood and the prior. And so if we want to complete our model, we have to add a prior. A particular conjugate prior that we could choose is an inverse gamma prior for sigma squared, and mu given sigma squared being normal. This is conjugate. What I mean by that is that if I have this prior and I have this likelihood, I can calculate the posterior exactly, and then I know the posterior. I don't have to do any approximation. And so now a real question for you that I'd like you to think about for just a moment again is, gosh, isn't this whole tutorial about approximate Bayesian inference? Why are we looking at a model, a super simple model, where we can calculate everything exactly? What was the point of that? Real question I'd like you to think about for just a second. Okay, so maybe a deeper question that we should all ask ourselves is, so we're approximating a posterior mean and a posterior variance, and we don't know the posterior. That's the setup of our problem. The setup of our problem is we don't know these values. How will we know our approximation method works? That's a tough question, because the whole point is we don't know. We don't know the answers. We don't know the ground truth. So something that we could do is we could look at an example where we do know the ground truth. We can compare it to an example where we do know the ground truth, and that's probably worth doing, and that's why we're doing it in this particular case. That's why we're looking at this super simple problem that's not super realistic. We're doing that. But of course, there's a problem with that. If we only look at that type of problem, we might be very biased, right? We might have a method that only works in super simple problems. So something that we're really going to be grappling with throughout this talk is, how do we evaluate? How do we know that we're doing the right thing? But it's something to keep in the back of your mind as we go forward. Okay, so something else that you should be very aware of and definitely take the time to realize is that the mean field assumption does not hold in the model. It is not a modeling assumption. Here is already a very first case, a very simple case where we can check, you can just immediately check that the posterior here does not factorize into some function that depends only on mu and some function that depends only on sigma squared. That's not the case. You can just check. There is no mean field assumption in the model. It's only in the approximation. Okay, so we are going to make this mean field assumption in our approximation, and we're going to choose to do coordinate descent. That's not super important here. Again, whatever optimization algorithm you want to use, you can use. But just for illustration's sake, we're going to do coordinate descent here. This is something that you can derive. You can also check against Bishop. I will just write the results for you to check against just to give you a sense of what this is going to look like. So we're going to have some distribution in mu that's defined by some parameters. Now, it's unfortunate, this overloading of the term parameters. These aren't parameters of the model in the way that we were talking about them before. They aren't unknowns of the model. They just describe the variational distribution. So we might call them something like variational parameters to distinguish. So we have some variational parameters for mu. We have some variational parameters for the distribution over sigma squared. And the way that we're going to do this is we're going to iterate between finding the distribution over mu, and then we find the distribution of sigma squared given the distribution of mu, and then back and forth and back and forth. And so that's one way that we could solve this problem, and we're just going to look at that for illustration's sake in this case. Okay, so again, a big thing to note here is that we are able to plot the exact posterior. That's not something that we expect to be able to do in any real problem. We are only able to do that here because we have this sort of unnaturally simple problem, but we can do it. So here we have the contours of the exact posterior. It's a distribution over mu and sigma squared inverse the precision. And we have to initialize our approximation somewhere, and our approximation, of course, is itself a distribution. Now, initialization is a tough problem. It's one we should think about. We're not going to think about it too hard right now. Okay, so now the question for you to think about on your own for just a moment is what is going to happen in the first step of this algorithm? Supposing we're doing coordinate descent, and the first step is we update the distribution in mu. So if we update the distribution in mu as our first step, what is going to change about this plot? Just think about that for a second. Okay, so if we're updating the distribution in mu, things will only change horizontally. Nothing's going to change vertically because the distribution in sigma squared has not changed. It's only the distribution in mu that has changed. Now, on the next step, we update the distribution in sigma squared, and this is what we get. We only now change things vertically. Also, it's worth noting that when we change things horizontally, the approximate distribution is getting closer to the exact distribution as desired. Same thing when we change things vertically, it's getting closer to the exact distribution. Now we can iterate back and forth, and eventually we get our full variational Bayes, mean field variational Bayes approximation to the exact posterior that's in red. Now in this case we happen to do coordinate descent, but I think what this illustrates in general is that if we're optimizing, if we're using any optimization procedure, what's happening is we're changing our approximating distribution, and hopefully to look more and more like our exact distribution. And that sort of visualization is very general. Okay, so this looks pretty good, as we said before. This looks like the means don't look too crazy. It looks like they're pretty similar. The variances look pretty similar between the exact and approximating distribution. So let's go on to a more realistic example to get a sense of, is that true in general? Okay, so now let's look at this microcredit experiment. So remember, microcredit are these small loans to individuals in impoverished areas, and we want to know, are they effective? So Rachel Meager has been doing some really interesting work on this. If you really care about microcredit, I really encourage you to check out her papers. They're very thoughtful. They're very interesting. They really go into depth in the modeling. We're going to be looking at a very simplified version of the interesting models that she uses. Okay, but there are really randomized controlled trials that went on in 7 different countries, ranging from Mexico to Ethiopia. And at each one of these sites, so each site is in a different country, a randomized controlled trial took place among 900 to 17,000 businesses, depending on the site. So each business was assigned microcredit or it was not assigned microcredit. And so we want to get at, was microcredit effective? And so perhaps a quantitative way to get at that is to say, well, how much did it increase business profit? And a priori, we don't know. Maybe it increased business profit, maybe it didn't, maybe it actually hurt. We want to find out. And so to that end, we imagine that we, well, in fact, we did, and by we, I mean, other people collected the actual data on the ground of what are the business profits. So y sub kn is the profit of the nth business at the kth site, which we can model independently as normal around some base business profit. Let's call it mu k. That's the base business profit at the kth site before microcredit happens. And then we have some term that has to do with microcredit. So TKN is an indicator function that says whether or not this business received microcredit. So it's 1 if the business received microcredit, it's 0 if the business did not receive microcredit. And so in particular, if it's 0, we just don't get this second term at all. And if it's 1, we do get the second term. And in particular, we get this microcredit effect tau. How much is microcredit increasing business profit at this site? This is really the parameter of interest for each site. This is what we want to know. Is tau positive? How positive? Is it 0? Is it negative? What is it? Okay, so we also have some noise here that we don't know for any particular site, and we want to learn that as well. So at this point, we have a bunch of unknowns. We have the mu's, we have the taus, we have the sigma squareds. We want to learn them, and so to complete our model, we're going to put some priors on these values. So in particular, the first thing that we're going to do is put a prior over the mu k's and the tau k's. So they're going to have some shared mean mu, that's sort of like the global base business profit, and some shared global microcredit effect tau. And so if anything, this is really the parameter of interest. Globally, what can we say about the effect of microcredit? How much is it increasing business profit? Now, this is incidentally another reason that Bayesian inference is useful for a problem like this. So we want to be able to share power across different countries, across different experiments in a way that respects that these are all different, but still allows us to learn something. And so instead of just analyzing all the data together and smushing it together, which doesn't respect that Mexico might be different from Ethiopia, we don't want to do that. We also don't want to just analyze the data from Mexico and then throw it out, analyze the data from Ethiopia and then throw it out, and so on, because now we're not learning anything across the different countries. We want to perform some sort of partial pooling, and that's what this kind of prior lets us do. Okay, so we put on some other priors. So this is a conjugate prior for sigma squared, the inverse gamma prior. We put a normal prior on mu and tau. C is a covariance matrix, and so the conjugate prior is inverse Wishart. But another choice that happens to have some nice properties is the separation and LKJ prior, so we can put that here. Okay, the point is what we have here is a model. It's a way more complex model than the model that we saw last time. It's a much more realistic model, the kind of thing that we might deal with in practice, and it's got a lot of parameters. It's got the mu's and the tau's and mu and tau without subscripts, the sigma squareds, the c's. We definitely can't solve this in closed form. Now we're going to need some kind of approximation, and so we have to ask ourselves, what is that going to look like? And in particular, we want to ask ourselves the question that we asked ourselves earlier: how do we know that it's working? How do we know that our approximation is working? Well, here's another idea for testing if our approximation is working. Maybe we think that we trust Markov-Chain Monte Carlo, and so we can test against that. Now, of course, eventually we'd like to not have to run Markov-Chain Monte Carlo. We'd like to have something that's just very fast that we can run on its own. Even in this case, if we use state-of-the-art Markov-Chain Monte Carlo probabilistic programming language, and we're very careful about how we set up the problem, it takes on the order of 45 minutes to get 2,500 draws, whereas mean field variational Bayes optimization takes far less than a minute. And so we'd like to be able to just run mean field variational Bayes. And in this case, things look pretty good. So what we're seeing here is that for each parameter of the model, so we have all those different parameters, we have a dot. And the estimate of the mean of that parameter from Markov-Chain Monte Carlo is the horizontal value, and for mean field variational Bayes is the vertical value. The line is x equals y, and so this is really agreeing very strongly. This looks very good. Okay, another thing that we can look at is Criteo released a very large data set on online advertising to the machine learning community. It's obfuscated, but it's open. And so something we might be interested in this case is conversion prediction. Are people going to click, or sorry, are they going to buy something after they click on an ad? Are they going to join an email list after they click on an ad? What are they going to do? We might also be interested in how predictive of conversion are different features, are different covariates of the model, are different aspects of this user, and how well do we know that? And this is the kind of problem that comes up in a lot of areas, not just online advertising. So in this case, we can use a logistic generalized linear mixed model. We're going to reduce the size of the data significantly in order to compare to Markov-Chain Monte Carlo. So again, that's sort of limiting us right now. So we're going to take a 62,000 subset of the data to compare to Markov-Chain Monte Carlo. And a first point that I want to make before we go on is another really fast optimization thing that we could do that I sort of mentioned earlier is map. The map estimate, the maximum a posteriori estimate. Why don't I just take the prior times the likelihood and maximize it? That's the same as maximizing the posterior. That's super fast. And so why don't we just do that to get our mean estimates? Well, let's suppose that we care about mean estimates, because that's the approach that we are taking in this talk. And let's suppose that we run map. Okay, well, that just takes 12 seconds. That's great. That's extremely fast. So why aren't we running map this whole time? Okay, well, in this particular case, we have a set of global parameters. So here in the first plot, we're plotting all the global parameters except for one that's called tau. And again, we have this x equals y line. We plot the mean estimate from Markov-Chain Monte Carlo versus the mean estimate from map. And yeah, a couple of these are a little off. So the reason that tau is separated is because if we write the x equals y line for tau, and we plot tau, it's so many orders of magnitude off that you can't even tell that the x equals y line is anything but a horizontal line. So that's pretty bad. And if we look at these local parameters in this model, and we use map to get those, and we compare to the Markov-Chain Monte Carlo mean estimates, we again see that we're just estimating them all to be the same value, even though they're not. And so if we care about these means, these are just completely off. And I guess we shouldn't be surprised by that, right? So if we're just taking a maximum, all you have to do is change distribution. All you have to do is just change your distribution a little bit somewhere, and that easily changes the maximum. It's not a very sort of robust thing to do. By contrast, in this case, mean field variational Bayes takes just 57 seconds. That's pretty fast. And we get great estimates of the mean. So here we're looking at all the global parameters. Now they're on the same plot because they can be. We look at this x equals y line. We look at the Markov-Chain-Monte Carlo estimate versus the mean field variational Bayes estimate, and it's looking really great. Same thing with the local parameters. And the reason that we'd like to avoid running Markov-Chain-Monte Carlo is that even for this very small subset of the total problem, it takes around 6 hours. Okay, so that looks pretty good. So it seems like, we ran a bunch of experiments on mean field variational Bayes to try to test if the means and the covariances that we reported were any good. And so we might say to ourselves, okay, well, we ran 3 experiments. That's like sort of the number of experiments that might be in a paper. Should that be enough? Are we ready to use mean field variational Bayes on every one of our problems going forward? Well, of course, something that you might have noticed is that I just said that we tested on the means and covariances, and that's not true. We just showed the means. We also just did 3 experiments. Is that enough? Is that enough to know that things are working in general? So let's ask ourselves a little bit more. Let's dig in a little bit deeper on these questions. Okay, so first of all, what about uncertainty? So remember, we're trying to minimize the KL divergence over this mean field variational Bayes assumption. And let's suppose that we have a very simple a simple exact posterior. Let's suppose it's multivariate normal. So multivariate normal, that seems like a very simple kind of situation. We're just plotting bivariate normal because, again, we can sort of only see in 2 dimensions. It seems like a very simple situation, but it's actually pretty realistic. So let's suppose, for instance, that you had conjugate linear regression. You have a linear regression problem with Gaussian noise. Or maybe you have, a Gaussian prior to go with it. Then the posterior you can calculate exactly. It's going to be Gaussian. Now, in this case, of course, you don't have to do any approximations. You don't have to do anything. But if you had changed either of those things slightly, if you had changed the normal assumption slightly, you might still get something that looks quite like this. Another big reason to think about Gaussians is the Bayesian central limit theorem, which tells us that as we get more data, our posterior looks more and more like a Gaussian. And so it seems like Gaussians are actually at least a somewhat realistic situation. And so here, if we look at this exact posterior, we suppose it's just the simple bivariate Gaussian, and we look at the mean field variational Bayes approximation, unfortunately, it's pretty badly underestimating the variance. So to see why that is, let's look at this KL divergence. So when P of theta given x, our exact posterior is pretty small, then if Q isn't very small, then we're going to get something that's pretty large, and we're not going to choose that Q to minimize our KL. And so in some sense, in some cartoonish sense, we're going to fit our approximating posterior inside our exact posterior. And so that's what's happening here when we have an axis line distribution that we're fitting inside our exact posterior. This is what we get. We're underestimating the variance. Now, this is really important if we really care about uncertainty. So, let's think about how might we be using uncertainties in practice. Let's say that you need an ambulance to the hospital. And you could take route A, which takes about 9 minutes, or you could take route B, that takes about 10 minutes. So on average, it's 9 minutes versus 10 minutes. You might think to yourself, gosh, I should always take route A, because that sounds a lot faster. Well, what if you need a life-saving procedure in 13 minutes, and this is 9 plus or minus 5, and this is 10 plus or minus 1? Now it suddenly seems like route B is actually preferable. You're much more certain to get to that hospital in time. Now, what if your estimating procedure erroneously told you, without support from the data, that this was 9 plus or minus 1? That's pretty scary, right? You want to really understand your uncertainty to make the right decisions, about which route you should take to the hospital. You don't want to be overly confident in a way that might really be hurting you down the road. And so this underestimating of the variance is doing exactly that. It's making us being overly confident. It might make us make wrong decisions. And of course, it gets arbitrarily bad as we increase the correlation of the Gaussian. We also don't get covariance estimates by construction. That's the mean field variational Bayes assumption. And this is something you can derive exactly. We don't need an approximation to do this particular derivation. And in fact, that's a useful thing to try out. Okay, So in fact, we can go back to those examples we saw before and ask, is this what was happening in those real life examples? And in fact, it was. So if we look at the mean field variational Bayes estimate of the standard deviation, the posterior standard deviation, this element of uncertainty for each of these different parameters, so we still have each parameter is a point, we now see that we're systematically underestimating the standard deviation relative to the exact posterior standard deviation, which we think we're getting from Markov-Chain Monte Carlo. And again, this could affect our decisions. You know, what if we found that the microcredit effect, how much is microcredit increasing business profits? What if we found that that was about $3 US purchasing power parity every 2 weeks? And we decided, maybe we're some multinational corporation, we decided we're going to invest in microcredit if the effect is sufficiently high and the mean is more than 2 standard deviations from 0. So we feel like this is, you know, a real effect that's really helping people. And so we would find that, in fact, the standard deviation, the posterior standard deviation, is the following. And so, in fact, the mean is 1.68 standard deviations from 0. So we would say, this didn't meet our threshold. We're not going to go ahead and invest. We're going to say instead that, you know, we're going to collect more data, maybe understand more about how covariates influence this. Like maybe if somebody has had a business before, that might affect whether microcredit will be a good investment, you know, various aspects of these individuals or the places that they're from. But if instead, in this case, we had used mean field variational Bayes, we would have underestimated that standard deviation. In fact, to the point that we would have erroneously, without support from the data, reported that the mean was more than 2 standard deviations from 0, and we might have rushed into this decision overconfidently, not in the way that we had actually planned to. Okay, and we say the same thing with the Criteo online ad situation. So here we are looking at these global parameters, and again, they're massively underestimating the uncertainties relative to ground truth. Okay, so is it just the uncertainties? Well, it turns out it's not. In fact, sometimes the means are wrong too. So here is a couple of plots from Bailey Fosdick's thesis, PhD thesis. So Professor Fosdick is really interested in understanding relational data, so graphs data. So we're interested in saying something about, you know, these networks where people are interacting and there's an edge or there's not an edge, and so we might want to model something like, you know, is there an edge or not? And this is a case where she really wants to be speeding things up. So for 1,000+ nodes, Markov-Chain Monte Carlo is taking over a day, and that's obviously not the scale of networks that people are really interested in. We really want to get beyond that. But if we run mean field variational Bayes in this case, we have the same plot as before. Each dot is a parameter, and we have this x equals y line in red. Some of these dots are not on that x equals y line. They're not being well estimated. And in fact, we can go a little bit further. For each parameter here, we can look at not just the mean, but a 95% credible interval, and we see that some of these mean estimates are outside the 95% credible interval. So in fact, they're particularly dangerous forms of the mean that's sort of bad on the scale of what we would assume to be a good estimate of the mean. Okay, so something else that we could say is, well, maybe we know a priori that there are certain types of models where this works and certain types of models where it doesn't, and then we just avoid the models where it doesn't work, and we use this for the models where it does work. And so just to examine that assumption, suppose that we have the following model. Suppose we're interested in doing something like predicting college GPA. And so we collect a bunch of standardized test scores, XN, you know, these are sort of our covariates in this case, and maybe we collect regional test scores as well, so these vary by region. And so our model might be something like a linear model. We say there's some linear dependence on the standardized test scores, what the GPA is, and some linear dependence on the regional test scores, but of course that linear dependence depends on your region, so that's K of n, that's the region. And so we put priors on everything because that's what we do. Here's a bunch of basically conjugate priors that you might choose, and now we have a full model. We have priors and we have likelihoods. And so we can ask ourselves, okay, how good are our mean estimates in this model? And what's nice about this model is we can just simulate from it again and again. And so we can test, you know, are we getting these mean estimates right? And so this is a little bit different than the results that we saw before. So now what we're saying is that we're looking at just one parameter, rho squared, but we're looking at different data sets. So over the 3 data sets that we simulated, so we simulated values of the parameters, and then we simulated points from those parameters, we can check, did the mean field variational Bayes mean agree with the Markov-Chain Monte Carlo mean? And it did for these 3 data sets. And so we might ask ourselves, does this mean that we can always trust this for this model? Is this model always going to be good? Now, we could simulate 97 more data sets, and it turns out that's not always the case, that some of these cases we are getting bad mean estimates. And so we can't just take this model-by-model approach. Okay, so what can we do? Well, we don't need to throw out the baby with the bathwater. It's still possible that even though we don't know in advance whether something's going to work, maybe the solution is to have a good diagnostic that tells us after the fact, did it work? And the hope would be that the diagnostic is fast relative to the full inference procedure, so it's something that we can use very practically. So I think this is a really interesting line of work. It's worth noting that it's non-trivial. So we said in the beginning that minimizing the KL is exactly the same as maximizing the elbow, and that's true. In the sense of, when you minimize the KL, you get the same thing as if you maximize the elbow. What's different is the values of those two things. So if you look at the value of the KL at your minimum, that tells you something. There's an absolute scale for KL. 0 is best and lower is better. And so if you're close to 0, that might be able to tell you something about your problem. Unfortunately, with the elbow, it does not tell you something about your problem. It will asymptote to something as you run your method, but that value won't necessarily tell you anything about how well you've done. It certainly doesn't have the absolute scale that the KL does. And so we need to do something like estimate the KL, or bound the KL, or consider some other type of evaluative mechanism. It doesn't have to be directly to do with that. So there's been a lot of really cool work in this area. I'm sure that my list is not exhaustive here, but I just want to point out at least some things. I also want to point out that there's at least one talk here at ICML with, I think, the very relevant name to our discussion, Yes, but Did It Work? Evaluating Variational Inference. So I'll just point that out. If somebody else is giving a talk at ICML on this subject, then I would love to hear that as well. I hope I didn't miss out anybody. Okay, so reliable diagnostics are a super interesting area. I think a really open area with a lot of potential for research to know, can we do something very fast, maybe very quick and dirty, and if we know that it worked out in the end, then that's fine. And if it didn't work out, then maybe we can go to something slower. And so this is, I think, a really, really interesting area to get involved with. But of course, we'd like to have both reliable diagnostics, if only because our code might be wrong, as well as methods that we can trust a priori, methods with theoretical guarantees a priori. And so it's worth thinking, how could we get that? Well, one method that we could do is we could sort of peel back this onion of assumptions that we made along the way. So for instance, we started by making this assumption of approximating the posterior. We said, what's the closest nice distribution? We've decided to make the variational Bayes assumption. We decided to make the mean field variational Bayes assumption. So we could ask ourselves, well, how about we use a richer nice set? How about we just don't limit ourselves to mean field variational Bayes? So an interesting observation in Turner and Sahani's 2011 paper is that, in fact, a richer nice set doesn't always do better on means and covariances. Beyond that, you can get, such rich nice sets that they cover everything, but in practice, that can introduce more headaches in terms of it could be longer for computing time. A nice thing about mean field variational Bayes is it's very fast. It could be more user time, could be harder to do. And a lot of the methods that exist right now that get richer in terms of the nice set introduce a lot of additional work, additional assumptions, additional approximations, and we need to know how good are those, just like we need to know how good are our approximations earlier. We could try alternative divergences, but that's going to have a lot of the same questions that we have here. Okay, so we really want theoretical guarantees on quality, and so for the second part of this talk, which I'm about to get into, I'm going to talk about a very different way that we might approach this. Instead of sort of thinking about variational Bayes and mean field variational Bayes and this particular type of optimization, maybe we can think of a pre-processing step, where first we take our data and we compress it in a very clever way into a smaller weighted data set, and then we run our approximate Bayesian inference algorithm on it. Can we get guarantees by doing that? So before I go into that, let me just point out some resources for variational Bayesian inference. So there are a lot of really great overview articles and textbooks, and I just really in particular want to point out David Mackay's book. So a lot of the classic examples in this talk and other textbooks really date back at least to that book. And it's been pretty much a timeless book, not just for Bayesian inference, but for a lot of machine learning. I also really want to point out Turner and Sahani's article, Two Problems with Variational Expectation Maximization. So one issue that I didn't get into here is multimodality. That's a really tough issue with a lot of subtlety to it. And I think that their article really deals with that subtlety in a very nice way. All of the experiments that did not come from textbooks or from Bailey-Fosdick's thesis, you can find in our papers with my PhD student Ryan Giordano down here. Okay, so with that, I'm going to go to the second part of the talk. I'm going to talk about just another direction that we could go, a different direction for thinking about how can we get these theoretical guarantees. How can we get something where we trust the results that we're getting a priori going into the analysis, or at least have some theoretical way to think about them. So let's just recap. We've talked about a lot of different applications where people are interested in Bayesian analysis, and in particular for the sciences and engineering and health and a lot of different sectors. We want something that we really do think is trustworthy, where we're not going to underestimate uncertainties. We're really going to get these uncertainties correctly estimated. And so we're imagining, again, the case where we have this prior and this likelihood, and we're trying to approximate the posterior. And so as a running example in this part of the talk, I'm just going to imagine that we have something like a classification problem. So in particular, let's imagine that maybe we have observed a lot of websites. So some of these websites are malicious. They're phishing for your personal information. And some of these websites are perfectly benign. They're just normal websites. And so for each website, we observe a set of covariates, a set of features, x sub n for the nth website, and we observe a label, y sub n, whether it's malicious or not. And we want to find a classifier. So in this simple example, we're interested in a classifier. And because we're being Bayesian here, we're not just going to get a point estimate. We're going to get a whole distribution. So in this case, it's two-dimensional. We can actually write out that exact posterior. We can draw it over here. And as we said before, we want to approximate this, but we want to approximate it in a way, ideally, that we have theoretical guarantees on quality. And so the proposal that we're going to explore in this part of the talk is summarizing our data as a pre-processing step before we run Bayesian inference, and ideally in a way that will get us theoretical guarantees on quality. And then if we combine this with another method that has those guarantees, like Markov-Chain Monte Carlo, then we should totally, in the end, have guarantees. And so the hope is to do this in a way that's fast, that's easy to use, that doesn't require deriving a bunch of different equations, in a way that gets us these error bounds that we want for the finite data that we have, in particular error bounds on the quality of means and covariances, posterior means and covariance estimates. Okay, so first I'm going to talk about getting at the core of the data set. How are we going to summarize this data set? We're going to try to get at its core. Now, what does that mean? Well, something that we could use to summarize our data set with a smaller data set is uniform data subsampling. That's a great way to deal with a very large data set. In fact, that's probably something that more people should be doing in general. It's very fast, it's very easy to use, but it'll turn out to not be enough, and we'll see what its sort of pitfalls are. Another thing that we could try is, well, maybe the uniformity of uniform subsampling is the problem. Maybe if we use some more careful importance weights, we'll do better. And we're going to see that there are some pitfalls there too. And so finally, we're going to try some optimization approach. Now, I want to emphasize this is a very different optimization approach than the ones that we talked about earlier. This won't be minimizing closeness over a set of nice distributions. It won't be something of the form of a map. It'll be a very different type of optimization to choose this core set. And then finally, we'll talk about another way we could summarize our data. So exponential families are a beautiful case where we don't have to do any really, really tough approximation for Bayesian inference. Things are very easy because of sufficient statistics. But of course, in general, we don't have sufficient statistics. So are there ways that we could come up with approximate sufficient statistics? Okay, so let's start thinking about the core of the data set. How can we get at that? Okay, so an observation that we can make is that a lot of times there are redundancies in data, even if it isn't traditionally tall, even if it's not just very, sort of low dimensional and just a ton of data about the same thing. So as a cartoon, imagine that I have a bunch of text data. Maybe it's sort of about sports articles. And so actually it's very complex and high dimensional, and I just can't represent that here, so please forgive the cartoon, and I have a ton of data. In particular, the World Cup is going on right now, so I imagine that there are a ton of articles about football. And maybe because it's not so close to the Winter Olympics anymore, there are fewer articles about curling. At least at the moment, it's maybe a less popular sport. And so I might think to myself, gosh, I want to run my machine learning algorithm on this data set, and it's very large, and that's going to be a pain. What would be nice is if I could run it on a much smaller data set. And maybe I could observe that actually amongst all of these football articles, there are a few that are pretty representative. And so maybe I could replace a large collection of similar football articles with one representative football article. And I'll just give it a really high weight because there were so many football articles to begin with. And maybe I could similarly replace many similar curling articles with one representative curling article, and I'll give it a low weight because there weren't so many curling articles to begin with. And then I would run my approximate Bayesian inference algorithm on this data set of size 2 or just a handful, and of course it would be super fast. You know, if you run any of these algorithms, you know that if you have a very small data set, things are going to be great, everything's going to be fast. But of course we don't just want it to be fast, we want it to be right. We want it to give us something useful. Okay, this idea of a core set, getting at the core of the data set, pre-processing your data to get a smaller weighted data set is not a new idea. It's an idea that came from the computational geometry and theoretical computer science community and has been around for a while. And what's awesome about the work in that community is that they're able to get theoretical guarantees on quality, that if they run their algorithms on this smaller weighted data set, they can get close to if they'd run on the full data set. And that's sort of our whole goal here. Okay, so why do we have to, do that? Why can't we use something that already exists? Certainly people have thought about summarizing their data before. Even in the Bayesian inference community, a number of people have thought about this. So there's data squashing for Bayesian logistic regression. If you do anything with Gaussian processes, you're familiar with inducing point methods for Gaussian processes. These are all very common. I'm sure there are more methods than what I'm putting up here, but you'll notice that these tend to be heuristic methods. They don't come with theoretical guarantees on the quality of these means and variances that we want to report at the end of the day. Okay, another idea is uniform subsampling. We'll come back to this a little bit more later, but let's just start by thinking about what might go wrong here. Let's suppose that I'm working for a curling manufacturer, and I want to work with them, and they want to advertise to the curling community, so they want me to do an analysis of these sports articles. And I think, oh, there's too many sports articles, so I'm going to uniformly subsample my sports articles, and oops, I lost all of the curling articles. Now, of course, in this case, maybe that's not the end of the world if we missed out on this curling advertisement. But you can imagine cases where this would really matter, right? So let's talk about cybersecurity. I don't maybe know actually what the malicious packets are in advance, and if I subsample my packets in a network, I might lose all of the malicious packets, or at least some interesting and important subset of them. Or if I'm in a medical situation and I subsample my data, I might lose a set of people who respond to a medicine in a very particular way, and that would be really bad. Okay, so that seems like a problem. And so we want to ask ourselves now, can we apply this to Bayesian inference? Now, it's not going to be as straightforward as using these methods that have been developed on things like k-means and minimum bounding box problems, because Bayesian inference has some very unique geometries. We want something that's going to work for whatever prior and whatever likelihood we throw at it. And so we want something that's going to work in general, and that's where the challenge comes in. Okay, so in order to think about how could we apply this to Bayesian inference, let's start by setting up the problem. What is a Bayesian core set going to look like? Well, remember, there are two ingredients that go into the posterior. We've talked about this a lot at this point. There's a prior and a likelihood. And if we're going to do something like summarize our data into a smaller weighted data set, that's pretty clearly going to affect one of these. It's the likelihood. Okay, so in that case, let's establish a little bit more notation. So starting on this line, I'm going to assume that our data is it's independent, conditional on the underlying parameter theta. So that is an assumption. It's a very common assumption. It's certainly true of the analyses that we've looked at so far, but it is an assumption. So once we do that, we can assume that we can write that the log likelihood is equal to this script L sub n. We'll define script L sub n to be that. And the total log likelihood script L will just be the sum of the individual data point log likelihoods. Okay, so now we can define a core set log likelihood. So in particular, the idea of the core set, remember, should be that it is a very small weighted subset of our total data. And so if we assign a weight to each data point, weight 1 to data point 1, weight 2 to data point 2, weight 3 to data point 3, and so on, and we collect all those weights in this vector W, then the zero norm of W should be much less than the total size of the data. The number of non-zero elements of W should be much less than the total size of the data. because we want to run our expensive Bayesian posterior inference algorithm on a very small subset of data. Okay, and so now we can define the core set log likelihood as a sparse sum of the individual log likelihoods. Remember, this should be sparse. Most of these terms should be 0. We shouldn't have to add them up. And we want this to be such that our core set log likelihood looks very much like our original log likelihood. In particular, for our theory, we're going to say that any Hilbert norm is fine in terms of looking at sort of the difference between the core set log likelihood function and the exact log likelihood function. But in our experiments, we use a weighted Fisher information distance that crucially puts a bound on the Wasserstein distance, a pretty tight bound. And the Wasserstein distance, in turn, puts a pretty tight bound on the posterior means and variances, our approximation to the posterior mean and our approximation to the posterior variance, which is sort of the goal. You know, we wanted to get good estimates of these things. Okay, so in some sense, this slide is about what do we want? You know, what do we want in life? We'd like to have these Bayesian core sets, but it doesn't tell us anything about how can we get them. How can we actually achieve these Bayesian core sets? So let's think a little bit about that now. Okay, again, I think a very, very reasonable first thing that we should think about, that we should always, you know, have as our first idea for dealing with a large data set is uniform subsampling. So let's think about a little bit more about what goes wrong there. Okay, well, one thing we said is that, oops, I might uniformly subsample away part of my data. Now, in a classification problem that's not very realistic, I would know not to subset away one of my subsample away one of my classes. But of course, I might subsample away an important part of one of my classes, as we discussed earlier. This idea of missing important data is actually related to a more subtle problem with uniform subsampling, which we can see in the following way. So let's suppose I have my full data set. I uniformly subsample it. I upweight the data so it looks like I have the full data set. And now I apply approximate Bayesian posterior inference, because that was the whole goal. I was going to get an approximate Bayesian posterior and compare it to my exact Bayesian posterior. Now, of course, I get a whole posterior. And here I'm just plotting the posterior mean, just because that's an easy visualization. But of course, there's a whole posterior there. And I could do this a few times. I could have my whole data set. I could uniformly subsample my data set. I could run my approximate Bayesian posterior inference algorithm. I could plot my approximate mean. And I could do this again. I could uniformly subsample my data. I could run my whole approximate Bayesian posterior algorithm. I could plot my approximate posterior mean. And here's where I want us to pause for a second. There is one exact posterior for the full data set. Our goal is to approximate that exact posterior for the full data set. These are meant to be 3 approximations of the mean. We don't even need to know what the exact mean is to know that at least 2 out of 3 of these are bad approximations because they don't even agree with each other. In fact, this is not just a cartoon. This issue of noisy estimates, we can see this in practice. So here what we're seeing in red and blue is 10,000 simulated data points. Now, we can take a Bayesian logistic regression model. So this is a classification model. We can uniformly subsample 10 data points amongst this data set. That's in black. We can run our approximate Bayesian posterior inference algorithm. In this case, it happens to be Markov chain Monte Carlo. We can plot our approximate Bayesian posterior mean, and we can do this 50 times. And if we do this, we see that we get these estimates of the mean that are just all over the place. They can't possibly be good estimates because they don't even agree with each other. Now, sure, I could increase the number of uniformly sampled points that I make, but that's not the point. I don't want to subsample almost as many data points as my full data set and then run Markov chain Monte Carlo on that. I want to run my expensive Bayesian posterior inference algorithm on a very, very small number of data points. That was the whole point, to speed things up. Okay, so it seems like uniform subsampling isn't cutting it, and we might ask ourselves, is there something else we could do? Well, certainly an observation we could make is that, at least in this particular cartoon, we know that we care about some of the data more than other parts of the data. Like in this cartoon, we say, oh, you know, actually, this fishing data is very important to us. We want to make sure that we don't miss out on that fishing data. That was the problem that we saw when we uniformly subsampled, is that we might miss some of that fishing data. So maybe there's a way to avoid that. So let's just recall what we're trying to do is we're trying to calculate this posterior, and that's too expensive. So what we'd like to do is we'd like to find this core set that represents our data such that when we run approximate posterior inference on it, it looks like if we had run it on the full data. And so what we're going to do now is we're going to say, well, what if we just put in some big importance weights on the phishing data? And now our hope would be maybe that, in fact, what we do is when we subsample, we tend to get a phishing data point because they have such high weights, and we tend to get a benign website because there were so many to begin with. And now we invert these weights to get the core set weights, and finally we run our approximate Bayesian inference algorithm on it, and we hope that this looks pretty good. So this is the goal. It turns out that we can actually solve for an optimal set of importance weights in this case. So let's say that the optimal weight for the nth data point is sigma sub n. It'll turn out that the optimal weight is proportional to the Hilbert norm applied to the individual data point's log likelihood. So we can just write out the proportionality constant. That'll be the sum over all of these individual Hilbert norms. And so just to recap, the idea here is we start with a collection of data. We find these importance weights. We sample according to these importance weights. And finally, we invert the weights to get the core set weights. So this is the proposal. The proposal is to do this form of importance sampling instead of uniform subsampling. And we might ask ourselves, is this a good idea? Well, we can get some theory that tells us how well we're going to do. So remember, we're interested in this error between the core set log likelihood and the exact log likelihood. We're going to get a high probability bound because we did that importance sampling to get our core set points here. Sigma is just that normalizing constant we saw before. Eta bar has to do with how well aligned the different log likelihoods are. And square root of m. So m is the number of points that we're subsampling. So sure, as we increase the number of points, this goes to 0, but something that you're probably pretty concerned about is that square root of m is just the Monte Carlo error. This is exactly the same error rate as for uniform subsampling. And in fact, we see that this doesn't look too good in practice. So in practice, we do the same thing as before. We have 10,000 data points. We subsample 10. Now we're doing it with importance sampling, and so they have different weights. That's what we see in black. We calculate approximate Bayesian inference on those 10 data points. We plot the mean. We do this 50 times. That's what we see in green. They don't agree with each other well at all. This seems pretty bad. We can increase the number of points that we importance sample, but that's not the point. We want to run our expensive Bayesian inference algorithm on a very small number of points, not a very large number of points. Okay, so what's going on here? What's the problem? So let's take a step back and think about what do we want. We want a good core set. We want to minimize this error in such a way that the W's are positive so it looks like a log likelihood, but also there are very few W's that are non-zero. This core set is very small. So to get a sense of what's going on, let's imagine an even simpler problem. Let's suppose that our data are just one-dimensional. So the YNs just exist in one dimension. In this case, we can actually plot the likelihood above each data point. So that's the curve in black. It's just Gaussian. And then the total likelihood, with a scaled log likelihood, because it's just scaled anyway, is going to be in blue. And you'll notice that there's a great core set here. There's a great core set of size 1. Just choose one of the points in the middle, and it's going to be almost a perfect approximation for that total log likelihood. And what importance sampling is doing is it's choosing these points according to the weights, and the weights are the thicknesses of the line. So it's doing exactly the opposite of this. It's not choosing the point in the middle. It's choosing the points way out to the sides. Why is it doing that? Why aren't we doing better? Well, let's simplify this problem even further. Let's not think of these likelihoods and log likelihoods as functions. Let's think of them as vectors. So essentially what we have is a sparse vector sum approximation problem. We have a vector for each log likelihood. They all sum up to the total log likelihood in blue, which is just scaled down a bit here. And there's a great core set of size 1. Just take one of those tiny points that are in the middle and give it a big weight. That would be a fantastic core set. But if we put all of our importance sampling weight on there and we sampled again and again and again, we would never do better than that point. What we really want to do is we want to find the point that's most aligned with the total log likelihood. And then we want to find the point that's most aligned with the residual. And then we want to find the point that's most aligned with the residual. And so the problem here is that we're independently sampling when we want to do is consider the residual error direction. And so instead of sampling, we might instead say, hey, this sounds like we're just trying to do sparse optimization, where the sparsity is that we want to pick up a small number of these points. Okay, so nowadays when you hear sparse optimization, so we're going to step away from sampling for the moment and think about optimization. When you hear sparse optimization, you think Frank Wolf. So let's just review what exactly is Frank Wolf. So in Frank Wolf, we're trying to optimize over a convex function. So that's the function that we see, this bowl, this f, this convex function. And we're trying to optimize over a polytope D. So x is in this polytope D. And so the first step is we choose the vertex that minimizes f, and then we repeat 3 steps on each iteration beyond that. So we take whatever point we're at right now, let's call it x, we find the gradient of f at x. That's this tangent hyperplane in brown. Now we say, what's the minimizing point on that tangent hyperplane? Well, that's got to be a vertex, because it's hyperplane optimized over a polytope. And then we do a line search between our existing point and that new point. And so if we think about it, we start at a vertex, then we do a convex combination with a new vertex, and then a convex combination with a new vertex, and a convex combination with a new vertex. And so after m-1 steps, we've picked up m vertices. And so if we could apply this to our problem, and if the vertices were the data points, then we could do pretty well. That would be the goal, is to pick up a small number of data points. Okay, so let's see if we can apply it to our problem. Well, our problem is to minimize this core set error, the error between the core set log likelihood and the exact log likelihood. We might as well minimize it squared. Now, if you've ever done optimization, if you've ever tried to optimize over some likelihood, you think, gosh, that's not a convex problem. But usually we're optimizing over the parameter. And here we're not optimizing over the parameter. We're optimizing over the weights. And remember, the core set log likelihood is linear in the weights. And so in fact, this is going to be a convex optimization problem in the weights. Okay, so now we ask ourselves, is this constraint set a polytope? Unfortunately, it is definitely not a polytope. We have that 0 norm there. But here's a way we can get around this. If we could come up with some constraint set that is a polytope, such that when we run it, each vertex corresponds to a data point, so we pick up m data points, and then we'll have satisfied this. And so here is an example of such a polytope. Each vertex corresponds to a data point. When all the weights are 1, which is the original data set, it satisfies this. The sigma and sigma n are those importance weights we saw before. And when we run this, if we pick up m data points, we automatically satisfy this 0 norm condition. So it's not a relaxation, it's that when we run Frank Wolf, we satisfy this condition. Okay, and when we do this, we can actually find that we get a theorem that tells us now that we don't decrease at a square root of m rate, we decrease at a rate that is exponential in m, which seems much better. And so now we want to ask ourselves, well, does this actually come through in practice? Okay, so let's start by looking at a very simple problem where we can calculate posteriors in closed form, so we can isolate what's the effect of the core set. So here we have 10,000 data points in gray. We have a conjugate normal model. We can apply uniform subsampling, that's in black, and the exact posterior predictive mean and 3 standard deviation interval is in blue. And so we run with our uniform subsample, we find these things, we do it 50 times, and we see that the estimates in green are all over the place. We can increase the number of uniformly subsampled points, but that's not the point. We want something where we run on a very small number of points, and in fact, we think there should be a great core set of size 1 here. Just pick that middle point. Okay, we can importance sample. We can choose importance sampling in this case, and we get the same problem. These are these very noisy estimates. And so instead of sampling, we can try Frank Wolf core sets. And so we're still doing 50 of these approximations. It's just that they all agree perfectly with the blue line in this case. The green lines agree with the blue line, and that's because it's doing the right thing. We see that for m equals 5, it's picking out that point in the middle that makes a fantastic core set. And then it's just slightly adjusting it. Sure, this gets better as we increase the number of points, but this is the point. We want things to be really good for a very small number of points. Okay, so we can look at other examples. Oh, let me first say, so another nice thing about this example is that we can calculate the actual KL divergence between the approximating posterior and the exact posterior, because everything's closed form here. And so we can see that, in fact, for any number of core set points, if we try any form of IID random sampling, like subsampling, uniform subsampling, importance sampling, that we're going to be getting orders of magnitude worse in terms of KL divergence, so this is a log scale, than if we use these Frank-Wolf core sets. Okay, we can look at logistic regression. So the first two rows are what we saw earlier. Nothing's changed there. But now, if we run Frank-Wolf to get these core sets, we get much better performance for a very small number of points. So for m equals 10, we're already getting less noise in our approximation than for m equals 1,000 with the subsampling methods. Another thing that's worth noting here is that this is really automatically picking up the geometry of the problem. So in the case of logistic regression, we see that what seems to be optimal is picking a point that's sort of perpendicular to this dividing line. We wouldn't want to be using something like k-means here. We wouldn't want to be using something like uniform sampling that would just get something in the middle. For this particular problem, we want to use the geometry of logistic regression. And what's nice is that we're getting this automatically. Okay, we can see this again for Poisson regression, for another example. So here our observations are integer valued. So we can pick out, again, 10 points, 100 points, 1,000 points, and we see that we get these much better estimates, these much less noisy estimates with these Frank-Wolf core sets. Okay, now something we should be concerned about, though, is that while we might be getting much better results for a small number of points, a smaller number of points with Frank-Wolf, it's more expensive to construct. And so is that time trade-off worth it? Is it worth it to spend that time constructing it? Because uniform subsampling is super easy to construct. So let's think a little bit about that. So here we have the total time spent construction and approximate Bayesian inference versus error. And we have a log scale in both cases. And we can compare uniform subsampling in red to Frank-Wolf core sets in gold. Looking at a number of real data sets, including actually a fishing data set, chemical reactivity, bicycle trips, airport delays. This is over also a few different models. Now we see that there are orders of magnitude improvements for a larger number of core set points, but towards the beginning it actually looks pretty similar. But it turns out that we don't need to have made that choice we did earlier for the polytope. That was just sort of a convenience so that we had a way that we could pick up a small number of core set points. If we're more careful about how we construct this optimization algorithm, we can actually do many orders of magnitude better with giga core sets, which I'll mention again briefly later. Okay, so let me just spend a little bit of our time remaining talking about an alternative way to summarize data before running some kind of approximate Bayesian inference algorithm, and that gets at sufficient statistics. So it is not always the case that Bayesian inference is a problem to run. In many cases, it's extremely fast, and those cases tend to be when we have exponential family likelihoods. So if we had an exponential family likelihood, we would be set. So let's just remember how things work with exponential families. So suppose our likelihood is the following. So we have our data, y1 through n. We have some covariates, xn for yn, and our parameter theta. And so we assume that our likelihood decomposes as a product over an exponential function of some function just of the data times some function just of the parameter. And the function just of the data we can call our sufficient statistic. Now, you might be used to this also having some normalizing constant after, but you'll notice that could also fit into this framework by just making the function just of the data 1. And so what's nice about the exponential family likelihood, what makes it so convenient, is that we can rewrite it as the exponential of a sum over these functions of the data times the function of the parameter. And so let's say that we're going to do something like Markov chain Monte Carlo. The way that Markov chain Monte Carlo is going to work is we're going to start at some parameter value. We're going to calculate the whole likelihood. So we're going to go through each data point to build up the whole likelihood. We're going to calculate that. So that'll be a time, linear operation with some constant, some large constant. And then we're going to go to the next step, and we're going to have a new parameter, and we have to calculate the whole likelihood again. And so what we can do here is if we had an exponential family likelihood, is we could pre-process, we could just sum up this data-specific term, And then when we're at any particular parameter, we just do what hopefully is a low-dimensional multiplication, and that's it. We don't have to do this whole sum over the whole data. And so this is sort of trivially scalable. It only requires a single pass through the data. It's trivially streaming. We can just keep adding things. It's trivially distributed. We can just add on different cores. And it's very complementary to Markov-Chain-Monte Carlo. So I'm not assuming that we have to have conjugacy here. We can have any type of prior that we want. It's just that MCMC is going to be super simple when we only have to deal with this low-dimensional representation of the data. Of course, the whole problem is that we don't always have sufficient statistics. We don't always have these nice exponential family likelihoods. So for instance, even in something as simple as Bayesian logistic regression, we don't have this particular form, this x of a function of the data times a function of the parameter. And so we have to go through and calculate this whole likelihood at every step. Same thing with other generalized linear models, with so-called deeper models. This is going to be a problem. And so we might ask ourselves, can we come up with some approximate notion of sufficient statistics? And in particular, we pursue a polynomial approximation because we know a lot about polynomials. We can say a lot about them theoretically. We know how they behave. So I'm not going to go into as much depth on this one, but I'll just mention that, again, now we can look at that Criteo data set that I mentioned earlier, but we can look at a lot more of it. So if we analyze 6 million data points in this case with 1,000 features, we inherit this trivial streamingness, this ease of distribution, this minimal communication from the sufficient statistics framework. We can run in 22 cores on this data set in 16 seconds, and we get these finite data Wasserstein guarantees, which is nice. Okay, so in this part of the talk, I've really focused on this idea of data summarization. The hope is that this could be a way that we could get methods that are scalable, that are automated. So certainly something that we were interested in, especially in the core sets case, was having something that works for a wide variety of priors and likelihoods. We want something where people can just say, what is your prior and likelihood? And then we can give them the means and variances that they're interested in. And in particular, we want to be able to get error bounds on those mean and variance estimates. So we talked about a couple of methods. One was this core sets idea, which I think is pretty general. Approximate sufficient statistics was more constrained to sort of the generalized linear model approach and in a couple of other ways. But it was very fast, and we saw some empirical results. Something that I'll also mention that's really nice, especially about the core sets framework, is that there's a way to sort of trade off, do this computational statistical trade-off, to trade off more computation investment for better performance, and that's by increasing the size of the core set. But I think this is just a start. I think that there are a lot of other ways that we could summarize data, a lot of ways to improve these ideas. I mean, even just going from Frank-Wolf core sets to Giga turned out to be a huge improvement, and that was just slightly tweaking the optimization approach. And so I think there's a lot of potential here. Okay, so let me just mention that if you're interested in this work, that you can check out a few of our papers. By the way, all of the slides for this tutorial will be available at the tutorial website with the URL up at the top there. You should also be able to find it off of the ICML main webpage. Let me highlight this paper in particular. If you're interested in this core sets idea, this summarizing data with core sets, this is a great place to start. Our earlier paper, core sets for scalable Bayesian logistic regression, was the first time we applied core sets to Bayesian inference. And this Giga paper here, the Campbell and Broderick Bayesian core set construction for greedy iterative geodesic ascent, which will be appearing at ICML here on Friday. Actually, so Trevor will be discussing the details of that. How does that work? So if you're interested in learning more about that, check out that talk. If you're interested in the polynomial approximate sufficient statistics work, then you can check out our NIPS 2017 paper. And we've also been exploring this idea of summarization in a couple of other different ways. And so one is for really highly combinatorial problems, maybe we can reduce the space that we're looking at. And then by being careful, we can get theoretical guarantees, again, on our posterior quality. And so this is something that Raj Agrawal will be presenting also on Friday at ICML. And so I just want to point out the members of my group, my research group, who are various first authors of works that I have presented today. And to conclude, I just want to point out, there are all these cases where people are using Bayesian inference. They're using it in day-to-day lives and important problems, important data analysis problems, and we want to provide them with methods that are fast and easy to use so they can focus on their important problems in biology and chemistry and economics and all of these different areas. And we want to do it in a way that's reliable because these are going to be making decisions that impact our lives, that impact the world. I also want to point out that there are some really interesting fundamental questions. There are a lot of open questions from what we discussed today. I think there's a lot that remains to be done, not just in terms of improving Bayesian inference, but in diagnosing Bayesian inference and knowing how well we're doing. But I think there's a really fundamental question here in how well can we do? Not just can we come up with some new method to make things better, but can we understand what's possible? What can be accomplished? Thank you.
So thank you, Tamara. And if there are any questions, I would appreciate that people can come to the mics, either in this corridor or over there.
Should I ask here?
Yes, please
okay.
do.
So I do not fully understand the pose or the problem of this Franken-Wolfe optimization. So as far as I remember, you want to optimize something like a norm between this small data likelihood and the full data likelihood. But before you must impose a model or like a statistical assumption for this. And you also have high parameters for this like statistical assumption. So how do you set these parameters?
Yeah.
Maybe.
So just to be So just to be clear, the nature of the problem that we imagine is that we're given a prior and we're given a likelihood, and so the likelihood is a full function over the parameters. I totally agree with you on that. But what we're optimizing is the difference between the core set log likelihood, which is still a full function over the parameters, and this full function over the parameters, the likelihood. So we're not choosing the parameters. We're saying that we have this full function over them, and we're optimizing this distance between those two functions of the parameters.
Okay, I think I'll ask you in person. It's easier.
Sure, yeah.
Okay, please, for people that is leaving the room, it would be nice if it could be a bit more quietly. Meanwhile, do we have any other question in the audience? So, okay.
In the earlier part of the talk, you talked about underestimating variances, and then you sort of seemed to open a question about possible solutions. And if I understood right, you suggested corsets with MCMC, which seems strange in a VB talk. Did I misunderstand, or? Yeah,
so this is one possible solution. There are other possible solutions. So we actually have some work on using linear response methods to correct variances in mean-field variational Bayes, but then those depend on the means being correct. And so we'd like to have something where we can say at the end of the day, here is some kind of theoretical guarantee on how close you are in your variance estimate. And so that's, something that we're aiming for.
Okay.
So one of the big problems with MCMC is initializing it and getting it to a point where once you start, you eventually find a place where it's good and you're generating lots of samples. So have you considered using variational Bayesian methods to propose an approximate distribution and then sample from that using MCMC to refine that solution?
Yeah, so I think this idea of initializing MCMC with a faster approximation is one that has certainly been proposed and, to the best of my knowledge, used by other practitioners. So also not even just variational Bayes, Laplace, things like this. And I think it's a great idea. I mean, also even just things like, more heuristic methods like k-means, basically any kind of sort of meaningful initialization can make a huge difference. I totally agree with you on that, yeah.
So it seems in the formulation of the Frank-Wolf optimization problem, the cost function, it seems like it requires an integration over all of the parameters again.
Yeah,
so how do you deal with that?
Yeah, so this is a great observation. So in fact, because these are two functions that we're comparing, we don't actually have access to this. We have to approximate it somehow. And so what we end up using in our experiments and what I show for the timing and the results and everything is a random features approximation. But that's one of many things where we have a bound about how well we're doing, and so we can combine those to get a total bound in the end on these means and variances. But I suspect it's one of the things that could absolutely be improved. I mean, in some sense, what has to be happening here is that we're bootstrapping our way to a better approximation in a little bit of a different way than the last question, but still doing that kind of thing. And so I think that, yeah, I think that's a great observation. It's certainly something that has to have an approximation there. How good is that? How much is that doing? You know, we have some bounds, but I bet they could be improved.
Thanks.
Hi, Tamara. Thanks very much for the tutorial. That was very lucid and well-structured. I just wanted to ask, stepping away from Bayesian modeling for a bit, have you tried exploring the idea of using core set-based subsampling on, say, a batch of data for gradient descent optimization, maybe, or even for subsampling experience in an RL setting?
Yeah, so we've definitely thought about core sets in other areas. Probably the one that we've thought about it, I think, at least somewhat successfully in is kernels, although we don't have anything quite up about that yet, but hopefully soon. I certainly think that there's nothing specific to Bayesian inference about it. And I think something that's really obvious about that is, well, it's been around before this for other types of problems, although they tend to be things like k-means and minimum bounding box. I think one thing that's a little bit tough about using it for something like stochastic gradient or anything like that is that, at least as it's formulated right now, you really do have to do a sweep through your data, and so it's not clear that the trade-off is worth it in those particular cases. But that doesn't mean that it's not possible. It's just sort of we haven't immediately found a way to make that trade-off work. But I think it's super interesting to think about these things, again, beyond Bayesian inference.
Thank you.
Hey, question. I'm wondering if you have anything to add regarding expectation propagation, which is basically variation Bayes, but what the KL divergence is used in the other direction.
Yeah, so again, you know, I think there are all kinds of interesting pieces of work that have been done for types of divergences that are not just KL, but expectation propagation points out a few of the similar challenges that we face in those divergences. So when we do KL in the other direction, first of all, we can't pull the trick that we pulled here. We have to make further approximations, and so you see that people typically aren't just directly optimizing the KL when they're doing expectation propagation. They're doing these other, you know, sort of cavity methods and things like that. Also, there are these tricky ways of understanding or not understanding exactly what's going on with these approximations. So sort of, I think one of the ways that people tend to think about expectation propagation and KL in the other direction is that they do things like overestimate the uncertainty rather than underestimate, which at first glance sounds better. At least we're not being, you know, overly confident. We're rushing into decisions. Maybe we're just being a bit more conservative. But unfortunately, that's not always the case. There are cases, even with KL in the other direction, where we actually can underestimate the uncertainty. For instance, in multimodal cases and things like that. We actually have a short workshop paper on this, I think, from 2016. But there is some sense in which I think we just don't fully understand what's going on in these cases, which isn't to say that we can't. I think I would see this more as a challenge, that we should work to come up with good diagnostics, with ways to understand fully what's going on in these cases. What do we know about means and variances? When can we trust them?
Thank you for the nice talk. I may be missing trivia, but it seems the core set pick up some small data set. But what do you think of the Bayesian central limit theorem? I mean, it requires the data the sample size to be infinite.
So let's see if I'm understanding your question correctly. So certainly the Bayesian central limit theorem will eventually kick in. But one thing that's a little bit challenging about it is that it does require the data set to be very large relative to the parameters. And I think in a lot of cases that people really are using Bayesian inference, that's not always the case, that there, at least for some parameters, is still a lot of uncertainty. It's also, by the way, worth making that distinction, that there can be some parameters that are extremely well estimated while still having uncertainty in other parts of the space. space. And so I think we're really interested in cases that even though they may have very large data, they might either be high dimensional, or there might be so many individual problems, or there might be some aspect of the problem that still has sufficient uncertainty that we don't even expect the Bayesian central limit theorem to have kicked in necessarily, much less that we are going to a point estimate.
So you mentioned diagnostics that you could use to determine whether the variational Bayes is working reasonably. Can you elaborate a bit more on what's already out there?
Yeah, so maybe I'll just mention a few things. So I think there's been a really interesting line of work that's been coming out in terms of understanding whether samples are coming from something like our exact posterior. And so that's something that can be, at least in theory, pretty easily adapted to variational inference. You just take samples from the variational posterior, and now you take a look at that. There's this paper that I mentioned that is coming out today that looks at some sort of unusual variant of importance sampling to check if variational inference is doing well. Let me see if there's a paper that uses this chi-squared bound on the elbow. And so what's nice about that is, as I said earlier, you can't just sort of infer much from the elbow about what's going on. In particular, you can't infer much about the KL value, but with this additional upper bound, you can say more about the KL value. At least you can bound it. Now, there still remains the question of, once you know the KL bound, how much do you really know about means and variances? But I think it's a really cool start.
Thank you very much.
Thanks.
Thanks for your tutorial. I'd like to ask, have you tried to use GPUs, those kind of tensor computation stuff, to accelerate the computation? Because
yeah, so I think there's in general a sort of meta interesting question here about how does Bayesian inference and the way that we do Bayesian inference interact with hardware. So in some sense, when you're doing a very sort of similar set of operations, again and again, there's a natural way to interact with hardware, to have hardware that's sort of optimized for that. And I feel like the way that at least we're exploring Bayesian inference right now is much less concentrated on that. There's sort of Markov chain Monte Carlo, which if you look at sort of the fundamental operations in that, end up being very different from what you would do for map versus what you would do for variational inference, or even what you would do for expectation propagation and things like that. And so I think it's not, at least as immediately clear to me, that there's an obvious hardware connection in the way that there are for other algorithms, but I think it's a really interesting set of questions.
Thank you.
Hi, thanks for your great talk. Is there a probabilistic interpretation of these upweighted samples that we're picking up in the Bayesian core sets?
Yeah, so I think there's so many open questions here, but I think one of them is definitely, what is the interpretation of these core set points? I mean, it seemed like there were some kind of really interesting things going on just from the visualizations that we saw. I think you could also think about, is there some way to just interpret these? Is there some interpretability aspect? I mean, certainly people think about that with k-means. I guess all of this is to say is I don't have an answer, but I think it's an interesting question worth pursuing.
And maybe a follow-up. Do you know how much outliers influence which core sets which core set points do we pick up?
Yeah, so I suspect that outliers aren't extremely influential, although, I mean, I'm basically just talking from my set of assumptions right now, not from any sort of serious study. I think they're influential to the extent that, they allow you to capture certain aspects of the data. So, hey, we got this point that was sort of perpendicular, but if that point hadn't existed, I think we would have found another point that looked like that. I don't think it's the kind of thing where we need the outliers, or that the outliers are necessarily super important, but if you're trying to capture what's going on in your data and there's an outlier and that's really sort of influential and significant to your posterior learning, then I think that you have to pick that up in order to really understand what's going on in your data. Yeah.
I was wondering if you could say more about the embedded geometry you get by taking the data points and mapping them into this functional space. Like the examples you showed where just one point would capture everything relevant were really compelling, but do you have any more texture there?
Yeah, I mean, I think the way that we have found most useful to think about this is really as a vector sum approximation, that fundamentally these functions are like vectors and we're adding them up, and so the extent to which we have intuition about vectors often follows through on this. There's probably a lot more to say there, but that has been pretty useful for us, I think.
Thank you.
Thank you for a great tutorial. At the beginning, early, you thought said that the model the prior and the likelihood would be built together with experts, and what are the ways to capture uncertainty resulting from model mismatch?
Yeah, so I mean, so even though we sort of were agnostic in this tutorial about the choice of the prior and likelihood, of course, in general, we often, in fact, we always think that they're going to be misspecified at least a little bit, that they're not going to be this perfect match. And so the question becomes, how important is that misspecification? And I think this is a really tough problem. I mean, fundamentally, on some level, what we'd like to do is we'd like to have some notion of global sensitivity. Like, here are all the priors and likelihoods that we could have chosen. What's sort of the range of outputs that we would have gotten over that? Hopefully, it doesn't range too much, in which case we feel like we have a robust analysis. And if it does range a lot, then maybe we feel our analysis isn't robust and we need to, think about it more or do that. I think one thing that's really important in this area, and this gets back at this idea of diagnostics, is just being able to tell when you have something that's robust or not. And so something that we've worked on separately is getting automatic notions of local sensitivity. Now, it's not what we want. What we really want is this global sensitivity over all these choices we could make. But I think that's a really hard problem. And so if we can at least get a notion of sort of, well, if I perturb things a little bit, if I perturb my prior and my likelihood a little bit, how much does that change things? And importantly, I think a really important point in all of this is that we want methods that are really easy. If somebody has to rerun an entire analysis, if they have to make derivations to get it, I think it's just not going to happen. If it's part of a probabilistic programming language, if it's part of the analysis that you get out for free, then it can, be something that's actually used, and that's what we're aiming for with these local sensitivity analyses. But overall, I think this is a really important set of questions: is how do we deal with model misspecification, how do we diagnose it, and how do we make sure that we're avoiding it?
Thank you.
Hey, I wanted to ask a question from a practitioner point of view. So I don't have a lot of experience with those Bayesian methods, but was the first part of your talk, was the purpose of that mainly to basically stress that mean field variational Bayes still has a lot of limitations that we should be aware of? Like, I'm just asking about your intention with that.
Yeah, so I guess my goal is to understand what we're using when we use our methods. I think we could have a similar discussion about any other method that you might use. So I think this is a sort of a meta point about machine learning methods, is that any method that you use is going to have places that it works, and it's going to have pitfalls. That's certainly true of MCMC. It's true of Markov chain Monte Carlo. It's true of mean field variational Bayes. It's true of expectation propagation. And so I think it's worth thinking, okay, let's take a method that's very popular. I would say mean field variational Bayes is very widely used, and let's examine what are the assumptions in that, when does it work, and when might it not work, and what should we as practitioners be wary of? What should we be attuned to? What are the things that we should be careful about in our own work? And something that I think is particularly important in this case is to separate out variational Bayes from mean field variational Bayes from your particular optimization algorithm. You could do a ton of different things for your optimization algorithm, but if there's fundamentally an issue with mean field variational Bayes, or there's fundamentally an issue with variational Bayes, you're never going to be able to solve it with the optimization algorithm. And so what I would hope that people would get from this part of the talk is what they should be aware of when they're using these methods, but also what they can expect to improve by changing aspects of those methods.
Thanks for that clarification.
Can you go to almost end of the talk when you show exponential family and Bayesian logistic regression is not a good case?
Let me just go back here.
You show exponential family. Oh, yes. So the likelihood, the last formula, I think it is also Bernoulli distribution.
Yeah, so it's a Bernoulli distribution with something that looks very familiar. It's that x of negative something of the data times theta. But the problem is you're not going to be able to just get this simple sum over the data functions when you multiply these particular terms. And that's what we're really looking for, that simple sum.
Okay. But you still can put, formalize the Bernoulli distribution at the end as the first formula in the screen, right?
I guess I'm not totally sure what the question is. Maybe we can talk offline afterwards.
Okay.
Thanks.
Hello. Thanks a lot for a great tutorial. So you didn't mention in your talk, but I'm wondering how easy would it be, or would it be possible to apply the idea of Bayesian concept to find the code of theta for multi-view learning? Because this problem would be even more challenging because we have big data, and then it's even more challenging to learn models, learn Bayesian inference for multi-view learning.
Yeah, I mean, I think it would be really interesting to apply this to a lot of other areas. So I think another area we've started getting into, not with exactly core sets, but these sort of data summarization techniques is Gaussian processes, so spatiotemporal models, things like that. I think there's a whole host of really interesting directions to go, and I agree that that's an interesting one. We just haven't explored it.
Okay, thank you.
Thanks.
Thanks for the talk. I want to ask, how much is the Frankfurt core set depends on initialization?
So in this case, it shouldn't depend very strongly on initialization because you start off by finding the best vertex, the best data point. So that's just going to be, you know, whatever it is. There's going to be one best data point, and then you go from there. And so in some sense, the initialization is sort of fixed.
Hi, thank you for the great talk. So I guess this is going to be a very broad question, but I find that this core set idea is actually pretty close to the active learning setting, where you're just trying to get a few examples of an unlabeled data set, and it seems like the best methodology right now are actually geometric based, so topological based. Was there an inspiration from these works that actually inspired you to do this, or is this just you stumbled randomly also on something which seems topological too, or?
Yeah, so in our case, the inspiration was entirely from this core sets literature from computational geometry and theoretical computer science. So it turns out that a lot of the people who originated this literature are also at CSAIL at MIT, so it's easy for us to go around the corner and talk to them. And so that was very convenient. But I'm not surprised that there are connections that look like this. I think there's something that seems very fundamental about this kind of idea. It seems very natural about this idea. And I think there are other connections to other parts of statistics, to machine learning, that are worth understanding better. And I think that's an interesting direction going forward. I hope that other people will get engaged in this as well.
Okay, so then from your team, nobody actually looked into active learning with this. Okay.
Yeah, we have not looked into active learning, but I mean, it sounds like a cool connection.
Cool. Thanks.
Thank you for the great talk. I have a question regarding for example, if you want to have a next step and go from the prediction of some distribution to the optimization of some parameters which affect it. For example, if you can, you have already identified that you can predict, for example, ambulance arrival time, kind of 10 minutes with a certain variation, etc. But now you want to, for example, decrease the mean, for example, and decrease the variance. How can you approach this problem within the variational Bayes framework?
So one thing that I would say that we were pretty focused on here was sort of understanding the posterior given a prior and a likelihood, but certainly doing something more active where we actually try to sort of decrease these things by changing some, picking up data points, things like that. I mean, this direction of looking at Gaussian processes is certainly related to things like Bayesian optimization and, where we pick up points and then we learn more about our functions. There might be more connections beyond that. I'm not sure if that answers your question.
Thank you.
Hey, how's it going? I just had a question if you had any opinions or thoughts. So there's been some recent work, I guess, in MCMC where you do mini-batch MCMC. And so MCMC has like asymptotic guarantees, which are nice, but variational inference, when you're converged, so there's the trade-off. So I was wondering if you have any thoughts into that?
Yeah, so my understanding is I think that Michael Betancourt had a paper that said that if we do mini batches with MCMC, at least under, I assume, certain conditions, that the mini batches have to be something like a constant times the size of the whole data, which seems limiting for the purposes of scalability. Now, there may be some nuance there that I'm missing, but at least my understanding is that that's at least one state of mini batch inference.
Okay, thanks.
Do we have any other question in the audience?
I have another one. So it's my understanding that the map mean parameters and covariance matrices of parameters are all dependent on the parameterization that you pick, and that kind of comes from on high. And it seems like you evaluated a lot of your work based on your ability to estimate these means and covariance parameters. Is that a meaningful way to evaluate it, or do you think you should be looking directly at the distributions that you're estimating?
Yeah, so I think there's a couple of interesting questions here. So one is, you know, what is the right way to look at a Bayesian posterior when we have that posterior at the end of the day? And I think there are challenges in this. So one is, yeah, I think I agree with you that we'd really like to look at the full Bayesian posterior, and I think there are fundamental challenges to that when we get into high-dimensional posteriors. I mean, honestly, even anything over 3 dimensions is just, it's hard to look at, it's hard to query. And so I think that at least one way that people deal with this is they look at means and covariances. Why posterior mean? Well, it has a lot of nice properties. So for instance, it's the Bayesian risk minimizing estimator. We know that it has these nice statistical properties. It's admissible from a frequentist perspective. And so at least it seems like there are reasons that we might be interested in a posterior mean. I certainly think that's not the only thing that we're interested in. Something that people often report, certainly on the uncertainty side, and we even saw this in Bailey Fosdick's work, was some form of quantiles, something like a credible interval. And so I think we could equally start from a talk where we start asking ourselves, okay, let's suppose that we care instead of about L2 error, which brings us into thinking about the mean, we care about L1 error, and then maybe we think about posterior medians, and maybe you think about posterior quantiles, and then we can think about, you know, to what extent can we guarantee that we're getting good estimates of that? And I think that's a tough problem. I think especially once you start getting into tail probabilities, I think that that's something we really, as a community, don't fully grasp and understand and know how to work with. You know, more than that, can we get beyond these summaries? Is there a really good way to really look at a Bayesian posterior distribution? I suspect that part of the answer to that is application dependent. Like, what are we trying to do at the end of the day? And so something that I think motivates us a lot is that we imagine that we're making some kind of decision. And for a decision theoretic framework, means are nice, again, just from a risk perspective, but also means and uncertainties help us make decisions. If we have a mean and uncertainty within some range, then maybe we might make a decision based on that. So we saw that earlier in something like an ambulance example or the microcredit example. But for whatever purpose we want to use the posterior, I think that's what really should inform what we're trying to report, what we're trying to do. And then we should ask ourselves from a theoretical perspective, are we reporting something that we feel confident in?
So it sounds like you're talking about means in your output space, and I think that all makes sense. But I was talking about means in the parameter space in theta. And as I understood...
So that is what I meant. So I meant posterior means. So means over so in the posterior we have a distribution over theta and then reporting a posterior mean.
I'm thinking about it from a supervised learning perspective.
Oh,
yes, okay, so everything is just these latent variables that you're trying to predict. So some of them, if they're like something about how fast an ambulance will arrive, certainly have an intuitive interpretation. But if they're just arbitrary parameters in a Bayesian model, some of them can't really be interpreted in any kind of linear way.
Yeah, in that case, though, I don't suspect that we care too much about their values, period. I mean, then, you know, we have to ask, what are we even doing with these? If we're not doing anything with them, then maybe we don't have to report the posterior, you know, sort of marginal in that direction. Thanks.
Okay, so any other question? Otherwise, I have a couple of questions. The first one is that, I mean, we have been talking about data summarization, and if you manage actually to reduce your data set size up to some level where you could actually run, instead of variational inference, MCMC, I was wondering whether you have, or there is any work studying the fact that instead of using your whole data set, you use the data summarization would actually affect the convergence properties of the MCMC, or even though whether you can assume anymore that asymptotically you are converging to the true posterior, which I believe you won't be, but whether you could quantify how far you are?
Yeah, so for the second one, I feel more confident answering that. So I think that the types of guarantees that we're getting are exactly on the exact posterior. We're saying, how close are we to the exact posterior mean? How close are we to the exact posterior covariance? And so we're not going to converge to the exact posterior, but we're going to converge to something that we have guarantees on how close we are in these summary statistics that we're talking about. And so I think from that perspective, if that's the thing that we care about, then we're good. And if there's something else that we care about, you know, relevant to like that last discussion that we were just having, then we should check, how close are we in that? And this is sort of the approach that we're taking also in this other paper that I mentioned that'll be appearing at ICML. Let me just go back to this idea that, maybe we don't have to converge to the exact posterior as long as the thing that we care about we're close to, as long as the thing that we're reporting at the end we're close to. And so we take that approach in this minimal IMAP paper as well, that we say, hey, let's do MCMC on this thing that isn't the exact posterior, but the things that we're going to report, things like edge probabilities at the end, as long as we can bound how close we are, then we feel like we're okay if that's the thing that we care about. So now I'm trying to remember what the first part of the question was. Oh, yes. What do we know about the properties of MCMC when we run this? That's a really interesting question. I think there's an interesting question that's maybe baked in here that's worth reflecting on that now that you say it, I would like to reflect on more, is when we have smaller data sets, certainly a trivial aspect of why MCMC is running faster is just any individual step in MCMC is faster. The iteration is faster because we don't have to go over the whole data set. But there are two aspects of MCMC, right? There's the cost of the iteration and there's the mixing time. And so does this affect the mixing time as well? I wouldn't be surprised if it might because, maybe by having this smaller, simpler data set, you have a different sort of geometry that you're exploring. But I couldn't say anything hard and fast about that right now, but I think it would be interesting to understand. Yeah.
Okay, and then the second question is a bit more related to the type of data. So for now, this data summarization approach seems to work for IID data, so where you can factorize the likelihood. So do you think, or do you have any idea of how this approach could be extended to some non-IID data where you have, for example, some temporal component going on there?
Yeah. So let me just first say that I'm very sanguine that this kind of thing should be able to be extended. I mean, that's the whole idea of inducing point methods, right? That, you can have these summaries of our data, even in cases where we have these highly complex dependencies in our parameter spaces, these spatiotemporal models, things like that. I don't think that what we're doing is specific to this IID data. I think that, again, something that makes me sanguine about this is that there is, I think that as long as there are cases where you think that there's fundamentally redundancy in your data, that you should be able to exploit it in this kind of way. The thing that I think I am less clear about, and this relates to sort of my final question at the end of this, is sure, we can do these things. We can summarize our data. And if there really is data to summarize, I think that we can make strides. But how well can we really expect to do? I mean, if I really have a Gaussian process where I really have all of this data that's, very spread out and really doing different things, maybe I shouldn't be able to do better than like the fully correlated, Gaussian matrix and everything, or covariance matrix. And so I think it's worth understanding, and I'd like to understand better, what are the fundamental limitations that we're facing in these problems? And I think it's a very related question to this type of problem.
Okay, thank you very much. So I believe that if there is no any other question, it's a perfect time to close the session. Do you have a question? Yes. Okay.
Thanks for taking the last one. I understand the computational effort is one of the main drivers for the methods that you're kind to share with us today, and that some of the hardware aspects from your previous answers are also relevant to discuss. My quick question is that when can I adapt your methods on Spark? And is there a open source toolkit that I could already pick up?
Yeah, so in terms of open source, thanks for asking that. Now I can plug us a little bit. So the code is all online, as is mentioned here. We're working with TensorFlow right now to get the core sets into basically Bayes flow and TensorFlow. And we've started talks with Stan about doing something there. Beyond that, if somebody's interested in talking with us, we're interested to talk more about integrating this somehow.
We are already over time, so let's thank Tamara again.
Thank you.